So let me start by providing a brief introduction. I am relatively new to CHIPS Alliance. I just joined in early January, and it's my pleasure to be part of this exciting community of folks participating in this. I have quite a bit of industrial experience going back through IBM, Sun Microsystems, Oracle. So I look forward to working with all of you. You know, if we look at the industrial evolution, we really have gone from what I would say was a soups to nut in-house type of experience. And that could be exhibited by companies such as General Motors, Ford Motors, General Electric, where I actually started my career a long time back, to AT&T, Digital Equipment, and IBM, where everything was done in-house, whether that be architecture, RTL, silicon processes, EDA, the whole thing was right there. So it was very convenient from the work perspective. But of course, that's a very high overhead for any particular company to maintain. So what that has evolved to more what I call a supply chain management type of thing, which you might see, for example, as Apple, AMD, or what I saw at Oracle/Sun, where you rely upon different suppliers to provide you different things, whether that be EDA tooling, and that might be particular IP that you license, say, from a IP developer, and of course from your foundry as well, that being through one of the major players that we all work with. And what we're seeing now happen is that we're going more towards an open collaboration type of environment where different companies may come together and collaborate on something, or as we are now promoting in CHIPS Alliance, is open source collaboration in the hardware space, which really will provide an entirely new ecosystem to bring forward the best ideas and IP that is shared and developed by the open source community that can be used to build interesting products. So if we look at compute and design challenges, I don't think it's any secret that the cost of hardware has increased significantly over time, right? It's just getting harder and harder. There's complexity on many fronts, whether that be architecture, RTL development and verification, the implementation, and of course the manufacture. It just takes a lot of time and money, or NRE, to get a product to the point where you tape it out. And when you do tape it out, of course, you want to make sure that is correct. And of course, in terms of innovation, we're really moving beyond the CPU and GPU type of environment. We're moving to specialty accelerators for machine learning, image processing, could be database accelerators as an example. So what CHIPS Alliance really is promoting or proposing is an open design ecosystem, right? That moves all the way from specification, RTL, open process design kits, tooling, physical implementation, and standards. And there's many potential contributors to this type of environment: individuals, universities, foundations, companies. What we're really trying to do is bring forward the best minds on very complex problems and to build a platform of innovation that all can contribute to and benefit from. If we look at the CHIPS Alliance, it's really an arena of pillars of interest and opportunities, right? It could be architecture, could be specification, could be implementation, could be tooling, could be verification. And there are others too as time goes forward, right? So it's providing a venue of collaboration. IP contribution from participants is welcome, but it's not required to join. So you can participate, but you don't have to donate IP to that. And the level of participation is up to you in terms of how much you want to put into it. And of course, as a result, what you get out of it too. If we look at the open source model, it's really about IP and innovation and then building your product, right? So we could start with an open IP catalog that's in the open source community. And then your innovation on top of that, or in conjunction with that, can yield a market differentiating product. And we have a number of areas where we already have had successful open collaboration, whether that be on the successful RISC-V implementation with the Swerf core. It could be the OmniExtend cache coherency protocol that you'll hear more about today during one of the talks, or it could be the AIBO 2.0 chiplets, which provides a standard mechanism for how to break your complex architecture down into smaller pieces that are better for manufacture, as an example. So far, what we've achieved with CHIPS Alliance so far is we have the 2.0 specification of AIB that we put out there, as I mentioned a bit earlier, and there's some details on it. And we also now have collaboration for OmniExtend between the RISC-V Alliance and also with chips. And we look forward to additional collaboration on that and helping to harden the architecture for many different particular uses. We also have recently formed an analog interest group, which is of interest to many different participants. That has characteristically been one of the most difficult arenas of chip design and is often the long pole in the development of any particular piece of silicon. In terms of goals of what we want to try to do in CHIPS Alliance, we're interested in increasing the membership. That's certainly a key goal. We want to get folks participant in it and take advantage of what we offer, and also to help have them contribute different ideas and to extend the ecosystem. I'd like to see increased collaboration, both in artificial intelligence, automotive, 5G. Those are some new arenas that we'd be happy to participate in. Of course, getting more IP contribution to the Alliance would be a benefit too. I think that's useful for everyone. And really provide a menu of choice for innovation, right? So that anyone can pick and pull different items from that to help build differentiated products. We also have quite a bit of interest in open tooling, as I mentioned earlier. So I just generically call it open EDA. That could be architectural simulation, RTL development, verification, analog, digital, FPGA type tooling. So there's a lot of opportunity there. And the other thing that I want to formulate this year as well is a university mentorship program and also a contest for students to participate in and to create excitement for the Alliance and also for different participants, right? In terms of both learning from a career perspective and also academically as well. So that, I'd just like to wrap it up and say, look forward to today's talk, and that hope it creates excitement for you, and that also interest in terms of joining the Alliance and what it can help do for you for your venue. So with that, I will introduce our first speaker, who is Professor Bora Nikolic at University of California at Berkeley. He is going to talk about Chipyard. Professor Nikolic has many interesting different activities under his research, is an expert in solid state circuit design. So with that, I'd like to turn it over to you, Professor Nikolic.
Thank you, Rob. Brian will be sharing the slides.
Just 1 second.
All right, thank you for the introduction. Right, so I'll give an update on Chipyard, which is our integrated design simulation implementation environment for RISC-V SoCs. To start, I would like to highlight that we are interested in designing generators rather than specific instances of IP blocks. Generators are there to enable us to specialize the design and lower the design costs through the reuse. We have two types of generators, digital and analog, and most of this talk will cover the digital generators, although I'll touch on the analog ones as well towards the end. Digital generators in our world are written in a language called Chisel, which stands for Constructing Hardware in Scala Embedded Language, which is essentially a piece of software when it gets executed, generates data flow graph that is a representation of the RTLs. It is not high-level synthesis. It is essentially writing HDL code in bit more powerful language, host language, in this case Scala. Version 3.4 is current, and Chisel translates to its intermediate form, which is called Fertile, and then from Fertile it emits Verilog and various kinds of design and verification collaterals. And Chisel originated in Berkeley, but over the past year has moved to Chips Alliance and is, the repository actually is hosted by the Chips Alliance. On the other hand, BAG is an open source Python-based framework for generating analog blocks. Everything we do is based on RISC-V ISA, which is an open and license-free ISA that most people are familiar with. It's important to keep in mind that ISA is different than the IP, so there are many research and commercial implementations of RISC-V cores out there. For example, there are well-known Pulpina cores, and there are Rocket cores that came from Berkeley. Rocket core is an example of a generator written in Chisel. We have practiced this for a while, so we have designed quite a few Chisel, plus some of them use the BAG as well, RISC-V chips over the years. Most of them have been published and are out there for people to take a look at. But in the process of doing that, we have generated a lot of open source components. These open source components include Chisel that I mentioned and its intermediate form Fertile and RISC-V ISA and the BAG Berkeley Analog Generator and various cores like the Boom core and the Rocket core and a good number of accelerators to go with that. And there are caches that have been contributed, that were designed in Berkeley, then contributed by Sci-Fi. There's TileLink also developed by Berkeley, then improved by Sci-Fi, Diplomacy from Sci-Fi, a number of peripherals from Berkeley and other places, configuration system, our flow tool, which is called Hammer. There is our FPGA simulation environment, which is called FireSim. And it became obvious that that whole thing is pretty disorganized and lives in a very large number of independent repositories that are moving independently of each other. It has become even hard for even for our students to put systems together from these different kind of components that not necessarily always fit with each other. So our goal has been to make it easy for small teams to design, integrate, and simulate complete SoCs based on open source. In order to do that, we went ahead and built Chipyard. Chipyard is a framework that enables us to put together many things that exist in the open source, primarily from Berkeley, but from many others as well. So they're grouped into these sections that involve tooling, which are the languages and the tools for bringing up RISC-V systems, then things associated with the Rocket chip, and the design flows that are targeting either software RTL simulation, FPGA simulation, or VLSI flows. BAG is not integrated in Chipyard, but we're working on that along with adding the BAG modules. When you talk about foundational components, we have RISC-V Rocket chip generator, which is essentially a parameterization system that enables to put together the SoC. Then there is Fertile and Chisel and Fertile, which has also comprises a large number of these Fertile passes, which are transformations that can be done on the intermediate form. All of them that we use are in the open source. So very briefly about what is in the Rocket chip. It is a parameterizable SoC generator that has a pretty good degree of parameterization. One can take various kinds of parameters and change them to their liking, or replace pieces of the generator with their own IP, including a separate core. Typical customizations involve, as I said, changing the parameters, adding coprocessors, or adding IP. Inside the Rocket chip, there is also a library of reusable SoC components where you'll find memory protocol converters, various kinds of arbiters and crossbar generators, and clock crossings and asynchronous queues. It is the largest open source Chisel code base. It has been used in industry. Sci5 is maintaining it. It was developed in Berkeley, but now primarily is maintained by Chips Alliance and Sci5, and it has been used in Sci5's products. When we look into what is inside of a rocket chip SoC, we'll find tiles, which are the units of replication for a core. So in our case, we can have our CPUs that are either Rocket or Berkeley out of order machine, or we, as an example of integrating Verilog source code, we have integrated ETH Zurich's Ariane, or what is now called CVA6. There are L1 caches and a page table marker in each of the tiles. Cache has a two-level cache system. There is a front bus that connects to the DMA devices, and there is a control bus that connects to the core complex devices, interrupt controllers, boot ROM, and the JTAG unit. Periphery bus connects to the other devices, and the system bus ties everything together. In order to integrate many of these generators, you have to have the right version that works with each of those. And we have built and tested many configurations that work together. For example, we have the cores that I mentioned, and then there is a number of accelerators that we have put out in the open source or adopted from the open source. So we have Aquacha, which is a custom, not standard RISC-V vector accelerator. Gemini is a machine learning matrix multiplication accelerator. There is an educational SHA accelerator that people can go through and quickly run through the exercise of integrating it in their design. And we have taken NVIDIA's NVDLA and integrated with our design. A memory system is Sci5's last level cache, and there is a number of peripherals that are out there that can be added. So when we customize this, there are many ways for customizing components and the entire SoC. So for example, one of the good examples that people can do in order to bring themselves up to speed is to configure a minimum configuration of the rocket core to build it as a controller core or a power management unit or system management unit. Then there are simple ROC accelerators. ROC is a standard coprocessor interface in RISC-V. And then we can add more complex ROC accelerators like Wacha and Gemini that I mentioned before. And then we can add many kinds of things. And on the bottom over here, there is a fairly complex SoC that has multiple cores with a heterogeneous coprocessors added to it. Now, it is important to have tooling that enables us to evaluate these kind of systems. So we have simulation implementation targets where we can target FPGAs in the cloud through our FireSim flow. We can just simulate, as software RTL simulation through behavioral Verilog, and we can have VLSI Verilog to drive the automated VLSI flow. So we start with our custom SoC configuration that we are customized for our target application. We put together the RTL generators, and then we go through the build process that targets any of these three possible flows. It's important to mention the thing that ties all of these together. It's RISC-V, and all of this would be meaningless without the software that would be running on it. So it is important to have compatible standard RISC-V tools and versions that are packaged with the Chipyard. So in this case, we start with that, and then we add our own ESP tools as a non-standard equivalent software tools package with that enable our custom accelerators to shine, for example, vector extensions or machine learning workloads. And then there is a libgloss for bare metal C-tests, and Fire Marshal is our internal tool that manages workload and Linux distributions. Of the updates of what has been happening over the past 6 to 9 months, Chipyard has been bumped to version 1.4, and here are a few highlights that may be of interest to people who are interested or are using Chipyard. First, OpenSBI has been integrated. That is, I believe, in Chisel. It originates from Western Digital, which is an open source implementation of a RISC-V supervisor binary interface that basically replaces Berkeley's bootloader. So this is something that has a much broader community supports than the BVL, but BVL is still an option for legacy implementations and legacy workloads. We implemented something that is called harness binders that are generally replacing something that is called IO binders, which were the generalized abstraction for IO interfaces from the chip perspective. And they have been, primarily IO binders have been targeting test chips, but we have found out that many people are interested not just in the test chips, they're interested in FPGA simulations and wanted to have a unified perspective on that as well. So harness binders generalize abstraction for IO interfaces from the test environment perspective, basically driving the chip from the outside world and making it work within its environment. We have pushed a few versions that enable local FPGA prototyping besides using this within FireSim, which works with cloud FPGAs in Amazon AWS. A lot of people have been interested in trying things out on a local FPGA. So we are supporting a very inexpensive FPGA, which is RT7, and a very big FPGA, which is VCU118. We have based a lot of this on Sci5's FPGA shells, but have added additional components to that, including the harness binders. We use this generally for simulation, but also for test chip bring up. And we are looking into adding future PCIe-based interfaces and FireSim support. Multi-clock operation has been dramatically improved, so it now supports diplomatic clocking and essentially the entire experience of building a multi-clock SoC has become a lot smoother. There has been, the generators have been made to work in a unified way or seamlessly move from FPGA emulation and simulation into ASIC designs. There was a number of relatively convenient features that have been added to that. We also have more of our VLSI tool flow has become visible by putting a lot of it into open source. So we have largely automated make file-based flow that takes the target RTL, target Verilog, and passes it through a set of commercial tools, as well as some of the open road tools to generate the DRC and LVS clean GDS file. When I said it is becoming more obvious what we are doing, most of that has been abstract. There have been a lot of obfuscations because we have been targeting commercial tools and NDA protected design kits. But now with Open Road and Skywater, we can actually publish most of that, and it is in the open source. And there is quite a bit of added documentation because we use it in classes. There has been a number of, as we were rolling out Chipyard, we have bumped a lot of these generators. Generally, Chipyard does not follow the bleeding edge of a generator. Probably a few months old, more mature generators are being integrated, so it is bumped to Chisel 3.4 and Fertile 1.4. It has educational solder cores, but one of the big updates was adding the Gemini 0.5 version, which is used for accelerating machine learning workloads. To start wrapping this up, we would like to enable complete mixed signal SoC integration. We have been building mixed signal SoCs based on Chipyard, but the integration of mixed signal blocks has not been automated, to say. It has been mostly mostly manual integration of automatically generated blocks. So we have these tools that I mentioned early on, which are BAG2 and BAG3, which are ways to generate mixed signal IP blocks. Majority of the existing generators are in the BAG2 version of Berkeley Analog Generator, and we have some fairly complex stuff that includes time-interleaved ADCs, high-speed SerDESs and PLLs, and they're targeting commercial technologies like TSMC 16, 28, Intel 22, or GlobalFoundries 14. We do have a BAG3 migration path. BAG3 is not backwards compatible to BAG2, but over the next few weeks, people may enjoy seeing some of these generators published completely in the open source in Sky 130. And there will be equivalent versions that will be targeting state-of-the-art technology kits in Intel 22 or GlobalFoundries 12. So, and this will be coming up in the next few weeks. We are working with the open source community. We are supporting open source EDA ecosystem and tooling. So we are targeting now SkyWater 130 flow that supports complete open source generator to GDS2 flow. And Hammer is there and is ready to accept any contributions that exist, that come up in this community. So in summary, we have already enjoyed quite a bit of a community support. We were very pleased to see in the RISC-V Summit in December, there were a couple of talks that presented their own innovations by using Chipyard. In education, we are using it successfully in 3 classes. We are using it in 3 classes in spring 2020, and we are using it in 4 classes during spring 2021. One of the very interesting examples is the Berkeley 192-290C course that is being taught this semester, where we have 20 students, majority of them being undergrads, as junior as third year undergrads. Bulk are 4th-year undergrads, some first-year PhD, and some master students. And none of them had any chip design experience. They took Chipyard, and they've took components from the Chipyard, added their custom stuff, ASC accelerator, AES accelerator, and Bluetooth transceiver. And that whole thing is going to be taped out in a month if they persist with that. So with that, we have quite a bit of a documentation. It's not as rich, but there are about 140 pages out there on Chipyard's documentation pages that enable people to get started. There is a number of tutorials. Some of them have been recorded and can be replayed. The one that is coming up soon is at ISCA 2021. Mailing list has 200 threads, and that is basically it. Everything that we have is in the open source. We are happy for people to use it. We are even happier if you put a PR with an improvement that you would like us to adopt. And to wrap it up, we have made it easy to design specialized SoCs. We have automated mapping into cloud FPGAs and ASICs, and we are targeting many of the commercial tools and commercial design kits, as well as SkyWater 130 with the Open Road. And I haven't done almost any of this work. It has been done by a number of our students. That leaves a few minutes for questions.
Thank you so much, Professor Nikolic, for an excellent presentation. I really do appreciate it. I have one question so far on the Q&A line, which I'll ask that first, and I'll ask with the follow-up question myself too, and appreciate if there's any from others. So question is, can local prototyping be done by distributing the target design over multiple FPGAs as occurs in FireSim on the cloud?
We are not supporting that yet. So we don't support multiple FPGA board, distributing and dividing up design in to multiple FPGAs, but we are looking into that. The idea of local FPGA prototyping was to enable these relatively small systems to be evaluated in the environment when they can work with peripheral devices.
Thank you. Another question just came in. Excuse me. Is Yosys being used for synthesis?
Yes, but not inside our integrated design flows yet.
Thank you. Sorry, go ahead.
I can elaborate on that. Go ahead.
Okay. I had another question that just came in, which is, does using Chipyard mean other EDA tools from different companies vanish soon?
That's a loaded question.
Yes, I was going to
Chipyard,
say that.
Chipyard does. Chipyard is mostly, if you look at it, what we have in there is a way to organize open source source code. What we do with that source code is up to us. We can go through commercial tool flows, and that's what we do. There are no completely open source FPGA tools that enable us to run through the FPGA flow in a completely open source way. So we will generally use, say Xilinx's closed source tools. In the VLSI flow, we have two options to go with Cadence's flow, which is what we mostly support and target NDA protected technologies. But we are now supporting an open source tools from Open Road and targeting completely open source Sky 130 kit. It is not completely stable. The release is not, there are gaps in those flows, but I think other speakers are going to address and tell us when are we going to see a stable release out there that anybody can take the source code for an SoC and make in a couple of days their own GDS.
Thank you. I have two more questions, and I think that's all we have time for. So first one is, do we have support for partial reconfiguration on FPGAs?
As long as that is permitted by the commercial tools.
Okay. And then the final question, actually, I have one more, Cam, and we'll try to get that too. Is there any possibility of adding verification methodology in Chipyard, like UVM, and where in the tool chain would you put that?
So we have that in works. There are system Verilog style assertions that are being added into the Chisel language. So stay tuned and you will see more of that. That will enable us to do for example, coverage analysis.
Very good.
And,
then
where does that live in Chipyard?
Go
That's basically trying to verify the interfaces. But go ahead.
Okay. And final question is, what steps or approaches are being taken to introduce Chisel into the industry? As a recent Chisel learner, I'm really impressed with the flexibility Chisel offers, but whenever I recommend someone to learn it, they are hesitant saying Verilog or SV are the industry standard, being system Verilog.
Yeah, that is true. We do have a boot camp that people can take over 5 days, and it is sitting in the open source. I can point people to that. People can take a boot camp and teach themselves Chisel. If you talk to our students, they really don't like, if you are 20-year-old, you really, our students that are 20 years old really don't like Verilog. They feel like that it's their grandparents' language, not their language. So I think the time will come when these changes are just going to become completely natural.
Very good. Well, thank you again, Professor Nikolic, for your excellent presentation, and also to the audience for your questions. I appreciate that. So with that, thank you.
Thank you.
So that we will move to our next speaker, which the topic is RISC-V Design Verification Workgroup Updates, and that will be presented by Matt Cockrell and co-authored by Tao Liu, both of Google.
Thank you, Rob. Can you hear me okay?
Yes, coming through
Perfect.
loud and clear.
Okay, and I can drive the slides. Perfect. The obligatory antitrust policy, then we can get to the agenda. So good morning or good evening, depending on where you are. My name is Matt Cockrell, and I'm joined today by Tao Liu and Udi Jangalada. We are pleased to give you an update on the RISC-V DV workgroup. We'll begin with an overview of the group itself, some attendance metrics, topics, and presentations that we've had over the past year, and some other updates on the group itself. Next, we'll go through an exciting update on the continuous integration platform that we've put together, then provide an update on the Python-based instruction generator. Tao introduced this in the last workgroup update, and today I'll go over an overview of where the tool is at this point and what we plan to do in 2021. Finally, we'll wrap up with a brief description of a feature we plan to add this year, support for the enhanced PMP, or what they call ePMP extension. But before we get to all that, we want to describe what the work group is aiming to accomplish. When we first started putting the work group together last year, we put together a bit of a mission statement to help kind of guide us on what we're trying to accomplish. So it goes that we create a forum for discussing CHIPS Alliance contributions that will provide or enhance verification platforms. The work group should strive to accept, support platforms that demonstrate compliance, functionality, and perhaps eventually performance. So in short, the current focus of the work group is the RISC-V DV tool that Tao has created. But in general, we want to foster discussions of all design verification related tools and platforms. So what's been happening in the work group up to this point? We've had 13 meetings. We first started last spring, right when all the pandemic craziness started. We average about 10 to 25 attendees in each of the meetings. We have participants from various parts of the industry. Simon from Paris joins us on a regular basis, and he gives us great insights on the tool from an ISS and other perspectives of some of what Paris's customers are looking for in the tool. We have numerous participants from Google, myself, Tao, and Uday being part of them. Also, the tool is used pretty heavily in the OpenTitan verification of the IBEX score, and so we have participants on that front too that come from Google. We have participants from Western Digital. They've used the tool for their RISC-V cores as well. Andes has been helping to develop support for the vector extension. So they have a lot to offer in that discussion. Doug and Amy from Metrics attend on a regular basis. They've had quite a bit to do with helping to get the continuous integration platform up and running. And Perfect VIPs has been large contributors to the Python-based flow. They consistently, attend to provide insight on development of the Python-based generator, as well as understand, the RISC-V DV tool and enhancements that can be made. In addition to just general discussion on RISC-V DV and other associated topics, we've had some great presentations from various presenters. A few of them, for instance, Olaf Kindren came in and he gave a great overview of Idealize and Fuse SOC, which was great in the context of integrating the RISC-V DV into different flows and automating those flows to make it easier to use in regressions. We also had the Open Hardware Group came in and gave us some great feedback on their use of the tool. They used RISC-V DV for validating one of their cores, the CV32E40P. As I mentioned, we also set up a CI platform, which has been great for just maintaining the health of the tool. I'll describe that a bit later. And we spun off another bi-weekly discussion on the Python-based flow, and I'll go into that in a bit more detail later as well. So the evolution. This is an updated version of the slide that Tao presented last September. As you can see, the tool has had a healthy evolution over the past few years. As we move into 2021, we want to continue the progress that we've had up to this point. We want to continue having the work group, on a regular basis, and grow the attendance so we can gather valuable feedback. We're going to, one of the top priorities for 2021 is bringing the tool up to compliance with the vector extension version 1.0. We've gotten some feedback that there's some users that would like to have that capability in the tool. And then we'll continue work on, and then we're going to add support for the enhanced PMP extension that's been proposed. And I'll talk about that a bit more later. So for those of you who aren't familiar with the tool, this is a high-level overview of how it works. So the tool takes in various inputs, such as processor configuration, supported instructions, whether it be integer, multiply, compressed, and so forth. And it generates a program that can be fed into an ISS and executed in a UVM system Verilog simulation environment. The outputs of the ISS and the simulation can be compared for correctness. If you have more interest in actually how the tool works, Tao has a great talk that you can view on YouTube. Also, there's a pretty straightforward tutorial on the GitHub that you can look at that will guide you in getting the tool up and running if you want to experiment with it. But if you have questions beyond that, I encourage you to join the work group and you can voice your questions there, and you'll certainly get some sort of answer. So the continuous integration platform. In the work group discussion, we determined it would be valuable to have a CI flow that would maintain the stability and health of the tool against the tool chain and make sure all of the contributions are keeping things intact and not breaking anything. So when we first shared this idea with the larger CHIPS Alliance forum, we got some feedback on how that should look. And ideally, it would be all totally free and open source, like hosted on a Travis, CI platform. But given that the tool needs like an industry standard system Verilog parser that can support UVM, that didn't seem practical. We needed an industry standard tool on the back end to make the CI flow work properly. So Google teamed up with Metrics to offer a cloud platform and then use their tool on that platform. Currently, the tool is only visible to a few administrators that are running the actual CI. Metrics has planned support for different types of visibility for their metric simulations and regressions. And so we're hoping in the future that we'll be able to provide that and share that with the rest of the community to show the health of the tool as it progresses and contributions are made. Now, an update on the Python-based instruction generator. In one of our first work group meetings, the question came up is, how do I use this RISC-V DV tool if I don't have a license from one of the large EDA vendors, Cadence, Synopsys, or another EDA vendor? And as I mentioned earlier, the UVM-based tool requires those types of tools from those vendors. So to address this, we decided to continue a previous effort we had in Google, which was to create a Python-based tool to enable a completely free and open source option for RISC-V processor verification. So in this flow, you could use the Python-based generator and feed it into a core that had a verilator model. So it would be completely free open source flow that anybody could use without any license obligations. So our approach includes using the PyVSC as the randomization and functional coverage framework. It's an open source package for generating random stimulus and collecting functional coverage. The syntax is familiar. It looks like system Verilog randomizing constraints and functional coverage syntax. And we are also using the same class structure as we did in the original tool. And this, we have the same randomization flow as we did with the system Verilog UVM tool. This makes the whole thing, seem familiar and allows for seamless integration with the existing end-to-end verification flow. So users that are familiar with the system Verilog-based RISC-V DV tool can seamlessly pivot to a Python-based generator if they would like to. This is an updated slide from the talk Tao gave in September that illustrates the collaboration between Perfect VIPs and Google. So essentially in parallel, Google did the PyVSC functional coverage definition, then the RV32i functional coverage and implementation. And Perfect VIPs did the PyVSC instruction class framework, then a basic implementation of the generator itself, and then they were able to generate a random program. That fed right into our end-to-end flow. So now any other enhancements made to the PyGen or the RISC-V DV PyFlow can be fed into our end-to-end integration flow to make sure it still works properly. Where are we at now? So as of now, we've implemented the instruction class and generator framework. The constrained random program generation is done with the ability to mix in random and directed instruction streams for RV32i, MCBFDA, also multi-heart program execution, and most directed streams are supported. We've implemented the RV32i coverage model for 32-bit instructions, and it's also been integrated into the end-to-end flow. Future work for this year includes support for 64-bit instructions, extending the functional coverage support for all instructions, support for different privilege levels, user supervisor, and eventually we want to reach full parity with the system Verilog-based generator.
We're just under the 5-minute mark.
Perfect. So the PMP enhancement, or ePMP. So for those of you that are not familiar with the proposal, the original PMP is meant to protect internal memory ranges. i.e. memory accesses are checked for access to a particular user or lesser privilege mode. But I'm summarizing from the proposal here, but with the current spec, if we want a PMP to be enforced on a non-machine mode and denied on a machine mode, so that we can only allow access to a memory region by a less privileged mode, the current PMP spec doesn't have that option. So the enhanced PMP, or ePMP, proposes a new CSR that can bypass, update, or enforce existing PMP rules. We plan to implement support for this in RISC-V DV for this register. We want this support to be modular so that we can maintain backwards compatibility with the original PMP spec. And we have an immediate use case that we can test this with the IBEX core for the OpenTitan root of trust chip. So in conclusion, we've made some great progress in the work group on, on the RISC-V DV tool. And we're adding a full open source capable solution in the RISC-V DV PyGen. In 2020, we want to continue that into 2021. The quality and the value of the contributions is a function of the feedback and guidance we get, in particular from the workgroup discussions. So if you have anything to add, please join us. There's a link to the mailing group here. That's what we use for the correspondence's agenda. If we have to cancel a meeting or postpone a meeting, we share that information through the mailing group. There's a link in the slides, and our next meeting is this Friday. So if there are any questions, I have Uday and Tower online to help me answer them.
Thank you so much. I really appreciate it. It was a very informative presentation, Matt. So we do have a couple of minutes for questions. So I don't have any from the audience yet, but I will kick off with one question. I was curious as to how continuous integration has worked in practice for you, and also if it leverages cloud computing.
So it does leverage cloud computing. It's actually hosted on Google Cloud instances. It's worked pretty good. We've had a few hiccups, and most of those were really just related to, I think, getting the proper accesses for GitHub so that metrics could pull, the top of tree version and fold it into the test bench that we were using. So it's worked pretty good. It's quite accommodating for access and things like that. But yeah, it's had a few hiccups, and we've worked through it, and it's been a bit of a learning experience.
Appreciate that. So, but we will be publishing the slides after the event. So for those that wish to refer to them, they will be out there. And I have a question from the audience, which is there any direct method to transform and execute the programs written in CPU-based Python program on RISC-V CPUs?
Do you want to take that one, Uday?
Sure, I can take that one. Yeah, so I think if I'm understanding the question correctly, basically the Python-based generator is just able to generate an assembly program as well, and that can directly be fed into an ISS and compiled and then loaded into a validated test bench as well. So the same execution methods are still available, but it's just you don't have to rely on having an EDA simulator that requires expensive licenses and so on to actually be able to use this. So the same methods of simulation are available as well.
Very good. And we have time for one final question, which is the Python flow faster to execute than the system Verilog flow?
I can take this one also. As of right now, we're actually experiencing some performance hiccups due to the PyVSC library that we're using, which is developed by an external GitHub contributor, basically. And so there's some issues with how it implements its randomization constraint solver, which is causing a lot of performance slowdowns. So as of right now, it is not, but we are actively working with the developer to figure out what exactly is going on internally with this constraint solver that's causing these problems.
Very good. And I have one final question I'll put in here since it came in. Is there any interest on making binding to use this instruction generator in other languages such as Go?
There's currently no plan for that. We're just focused on the Python-based flow and the system Verilog-based flow. There may be some performance gains with Go, I would imagine, but we haven't looked at that yet.
Very good. Well, thank you so much for your presentation. I really appreciate your sharing it with it and taking the time to prepare it as well. So thank you again.
Thanks, Rob.
Our next presentation is open source flows and ASIC and FPGA tool development. Michael Gilda will be presenting. He is with Ant Micro. So Michael?
Hello, can you hear me?
Yes.
Perfect. Should I turn the video on? It seems like it's locked. So I'll just skip that.
We have not, you don't have to. It's up to
Okay.
you.
Let me share my desktop. Hopefully you can see this. Okay.
Yes.
Today I'm going to tell you a few words about open source flows for ASICs and FPGAs and kind of how to get there. Because of course it's not all possible today, but we're going to certainly make it happen with Chips Alliance. A few words about my company. We are effectively kind of an open source business that kind of flourishes in building new workflows and new design methodologies based on open source, and then we use them to build products for our customers in various fields. And so we span a wide range of hardware, software stuff, but of course today we're also going to specifically focus on FPGAs and ASICs as well as tooling. Which is, of course, a big chunk of our work for our clients. And if you want to learn more about what we do in general, you can take a look at the technology showcase at our main website. Just scroll down on the main website, and you're going to see a lot of open source related blog notes about various things. So now, how can you actually enable faster innovation? How can you enable more of it in this pretty complex space? So Chips Alliance is trying to achieve that with various activities, and I chose to break it down into 5 groups of things. So how do we enable those open source flows? How do we kind of help people scale into real life projects in ASIC and FPGA development? First up, I'm going to talk about enabling scalable and hybrid cloud computation. Which is necessary, of course, for just kind of making these very heavy flows work. Secondly, broadening the outreach to cover, more people that can be attracted to this very interesting space, which is currently, of course, a little bit niche as compared to other things. Thirdly, bridging things that already exist, but perhaps haven't really been benefiting much from the open source innovation. We do want to kind of make sure that these things don't get left behind. Then it's about, breaking down complexity, so kind of making things easier to partition into smaller chunks so that you can handle smaller problems instead of having to tackle everything at once. And the last part will be about enabling collaboration, which is, of course, everything we do is related to enabling more collaboration, but more specifically, the tools and the projects that focus on that part. And Chips Alliance is trying to approach this problem in a very complex way and address all of those challenges at the same time. So starting with enabling computation at scale for EDA development, we've been working with Google and others to enable the workflows that are needed in the cloud to build complex designs. And of course, as you know, EDA related flows take up a lot of time and complexity, and they involve a lot of tools, many of which are not open source. So the challenge here is that you need to combine various things coming from various worlds. You need to make sure that these things scale well. You need to be able to share and analyze results without exposing everything that you have internally, perhaps. And you need, good packaging and quality of results. And all of this is necessary to scale it out. So I'm going to talk a little bit about one of the things that we've been doing related to enabling hybrid setups that allow you to do public CI, that also employ internal compute resources in your compute data center. And this is based on GitHub Actions, which is, of course, the GitHub CI system. And we've enabled custom runners in GitHub Actions, which basically allows you to run some stuff internally and then make that publicly available as part of CI with the results being fully open. And this was created, of course, out of the need that our ASIC and FPGA flows have been generating, because using whatever's offered to you by GitHub by default is not really enough to run all those long-running flows. And also the configurability, the customizability of what GitHub Actions would offer you by default is definitely less than what we need. So the flexibility offered by custom runners is really useful. And what we've done is we've enabled containerized builds with virtualizations inside our own cloud. We've also made it work with Google Cloud because it's a collaborative project with them. So you can essentially manage jobs in between, the default runners that you get from GitHub, but also on-premise runners as well as Google Cloud-based runners. We've also integrated with Google's Build Event Server, which I'm going to talk about in the next slide, as well as we're working on a number of other improvements to make it possible to scale out the development of ASICs and FPGAs using cloud technology. I mentioned the Build Event Server protocol, and generally speaking, sharing of results with other people. So of course, all those heavy flows need some kind of ability to present and analyze whatever you've done. And we've been implementing bits and pieces that were needed to help integrative systems such as the Google Build Event Server, so that you can basically take those results of your CI, be it an internal CI or perhaps this GitHub Actions CI with the custom runner integration, and pushing it to whatever sync that gathers the results and enables other people to view them. We can enable custom visualizations like usage of resources, viewing of artifacts in specific ways. We can have unlimited storage, both in terms of amount of storage, but as well as the time we can store results for. And generally speaking, this is a very vibrant space. The BESS protocol itself was created for Bazel, which is also a very interesting tool that's kind of taking up some adoption in this space. Check out that link later to learn more. But basically, Bazel enables you to reuse repeatable build results whenever things don't change. Another thing I want to talk about in this chunk of my presentation is about containerization, about packaging. So in order to enable people to use the tools that we're working on, you need stable, reproducible builds. You need stuff that you can just download and start working with. So we've been working on packaging things into Docker containers, into Conda. It's a very, of course, large endeavor that takes a lot of people, and it's a collaboration. So we're working on some aspects of this. Google, eFabless, and people like Unai and Martinez Coral are helping out. And generally speaking, it's a very vibrant community that we're building there with the help of chips. You can take a look at the HDL organization on GitHub. That's where you'll find many of our packaging-related stuff. Also, we've been working a lot on Edelweiss, together with Olaf, of course, and the FAST Foundation. If anyone doesn't know Edelweiss yet, it's a Python-based framework for interfacing with various tools for ASICs, for FPGAs. So basically, a nice way to abstract out your flow, which is a very important thing if you're going to make that flow at least partially open source and potentially fully open source in the future. So the next thing you need to do to actually enable all those open source flows is making sure that you invite the right people to the table, that you brought in the outreach. And basically, we were looking at how to really make open source ASIC design happen. And ironically, part of that is that you need to make ASICs more like software, because software is the very vibrant space that you want to attract talent from. You want to attract this innovation and new ways of thinking about design. So FPGAs is one thing that enable that. New HDLs and new methodologies is another. The FPGAs are actually an important entry point into ASICs. A lot of people that get interested in ASICs, they can't really build an ASIC at home, so instead they go into FPGAs. But the flows in FPGA are also closed. And it's a fairly niche technology anyway, as compared to system on chips. So we're kind of trying to change that, and we're trying to make sure that FPGAs are also open, because open source FPGA design, open source development boards are key to generating enthusiasm about ASICs. And you can take a look at the RISC-V contest example that we organized a few years ago, how you can make that happen by going into ASIC through FPGA. So of course, SimFlow is one of the key projects in this space. It's a fully open source toolchain for FPGA development, and we want to provide an end-to-end and vendor-neutral flow, because of course you want to pool those engineers from all those islands of platforms that they're working on. We want to make FPGA development more software-centric with SimFlow, more collaborative, and we've already accomplished a lot of cool stuff, especially in niche scenarios, specific scenarios where SimFlow can definitely do some magic. And more generally, it just enables people to get started quickly with a board and not having to download all those heavy proprietary tools. So we also want open tools to kind of make FPGA just mundane. We want to make them something that you just use for a configurable silicon, because why not? And one of the successes we've had here in this space is the collaboration with QuickLogic, where we've developed an open source toolchain with their support, which is kind of first in the industry. The toolchain, of course, was the key part, but like we also enable a lot of other things and bridged a lot of communities. We enabled Zephyr RTOS, ported open IPs, created Renode support, and so on and so on. It's a very important kind of comprehensive aspect to this that eventually enabled a lot of excitement, a lot of projects that built on top of that. And there's some great things coming up that I'm not going to describe today, but watch this space with interest.
We're just under 5 minutes.
Okay, another thing that needs to be mentioned is, FPGA-related tools related both to programming FPGAs, but also creating new FPGA silicon. And we want to make, with things like OpenFPGA and Verilux routing, we want to make FPGAs just much more widespread. And last thing I want to mention here is Chisel, of course, and all the related work in new HDLs. All those ideas that you can borrow from mainstream software development are kind of channeled through things like Chisel into other areas and Chips Alliance in general. We have a working group for Chisel that is a vibrant space for this kind of development. Bora has already described a lot of this. Okay, we have new methodologies and we want to enable new people, but how do we kind of also reuse whatever has been done before? We need to bridge existing things. So we need to make it easy to combine and remix stuff that already exists. And we saw a problem here, namely, there's a lot of great open source tools that could bring value into ASIC design, but unfortunately, it wasn't so easy to interface them with, for example, System Verilog, which is broadly used in the industry. So we've been kind of tackling that problem, and we have great progress here. So why would you need open source System Verilog support? Well, a lot of groups use System Verilog, OpenTitan, Chips Alliance, Western Digital. Designs like Swerf and IBEX are in System Verilog, so we just need to somehow make it happen. And also the RISC-V DV update probably kind of made you realize that it's an important thing. And we basically took this approach where we can first measure. So we've created a test suite for System Verilog tools that we can kind of measure the current support of System Verilog in various open source tools. And you can go to SVTests, the links here to see a dashboard that we can generate to show the current support. But of course, that's the dashboard. But of course, we've also been working on improving the situation. And together with Google and the low-risk and OpenTitan teams, we've been actually working on projects such as Sherlock and UHDM, where we have really great successes. We've been able to simulate and synthesize the OpenTitan designs with fully open source tools. You can take a look at that on GitHub. So that's a diagram of how it works, uses the UHDM library. Also, if you want to do linting and formatting of System Verilog code, you can actually do it with open source tools now using Variable, Google's open source linter formatter for System Verilog, which we've been also very actively developing. And you can generate very interesting stuff from that using tools like Kythe. So there's a lot of activity in this space. The last thing in this section is about open source UVM, which we're trying to enable together with Western Digital and Chips Alliance in general. We're implementing dynamic scheduling in Verilator, which is the first step to getting, partial UVM support, and we've very good progress. So watch this space as well for updates very soon about being able to do some simple UVM stuff, hopefully. You also need to, of course, break down complexity to make sure that people can actually get into this space easily. And one of the ways that you do that can be bringing, breaking designs into chunks and eliminating vendor lock-in. So we've been working on projects that enable, rapid innovation in this space. There's still a lot of things happening, but not so much open source actual implementation, which I think tools like AIB and frameworks like AIB are trying to change. So great kudos to Intel for releasing their AIB chiplet specification as well as implementation into the Chips Alliance. There's going to be a talk about this later today. but it's a great, high performance chiplet implementation that's being adopted. It's already used in DARPA, kind of advertised in some of the upcoming DARPA projects where you need to develop a AIB compatible chiplet. We've just released 2.0 version of the specification at Chips Alliance. So definitely AIB is a shining example of how you can make collaboration happen in this very difficult, admittedly, space. And we need more of that kind of activity to break down complexity of big chip designs. One of the things that we've been doing ourselves is also a simulator called Renode that is enabling people to create designs from building blocks and do various interesting things and simulate entire SoCs before actually implementing them. And we've been enabling things like co-simulation with Verilator to quickly prototype different solutions. We've been, of course, also implementing co-simulation with physical FPGAs. That's also a way to break down the complexity and bring in software developers into this space and make sure the problems we're trying to tackle are easier. And the last part, and I'll be kind of winding down this talk with how do we enable collaboration, and I think that's kind of course, the most important part. RISC-V has demonstrated, of course, that ASIC design can be collaborative, but in order to make that happen, we need a lot more than just cores. We need tooling, we need building blocks, and that's what Chips Alliance is tackling. And specifically reuse and collaboration is something we want to bring over into hardware from software. One of the things that you'll also hear about today is the open source PDK. It's a wide collaboration between multiple entities, and it's the first, open source PDK. Even though it's 130 nanometer, this is a very, very important thing to happen because this enables open sourcing other things. Wherever you have tools interfacing PDKs, all of that stuff is typically very closed and very proprietary. And without an open source PDK, it's very hard to create examples that can be actually used to manufacture chips. That can be published online without problems. Skywater PDK is solving that, and watch out, there's going to be more in that space. There's going to be a 90 nanometer PDK upcoming and better stuff after that. So definitely listen to Tim Ansell's talks later. On top of the open source PDK, there's an open trial program. People can make chips and it's free for them. There's been dozens of participants, including, of course, Micro, building various RISC-V, Open Power, Swerf, cores, you name it. There's an aim to kickstart an open source ecosystem that can actually build chips, not just talk about them. And all of this is enabled by the Skywater PDK. And of course, this talk wouldn't be complete without mentioning OpenRoad, which is, fully open flow that you're also going to hear more about today from Andrew Kang and Tom Spiro, so I won't get into details. And of course, you need open source IP, but that's perhaps a topic for yet another talk. One of the things that have happened very recently, and I think it's worth sharing, we've just established an analog working group. So we're not just about digital design. It's also mixed signal, it's also analog. There's a huge interest to collaborate in this space. And we've just onboarded our first project. We're just onboarding our first project, OpenFASOC, which is also associated with OpenRoad and DARPA programs. This is led by University of Michigan, as well as University of Virginia and ARM. So this is a fully open flow, as open as it gets perhaps at this point, with both a focus on digital but also analog, and we want more analog related tools in Chips Alliance to make sure that the entire space is covered. So summarizing, there's a lot of work to be done, but a lot of stuff is going really well. We need this collaboration between the ASIC and the FPGA design space, and Chips Alliance is playing a key role in this. You can also get support in building real stuff in this space. If you want to do that, go and talk to us. We can help you get commercial support, integrate tools, and implement real-life use cases. And through this, we can, of course, improve the ecosystem. So happy to talk to you afterwards. Thank you very much. That's all from me.
Thank you so much, Michael. I really appreciate the informative talk. So I would encourage folks who might have questions to follow up with Michael offline, as I want to make sure we try to stay on schedule here. But thank you again so much for sharing your chat. It was very, very good. The next talk is, in fact, about the AIB chiplet ecosystem that Dave Kellett will be sharing from Intel. I think this is a very interesting technology that they have put into the open source community, and I think it really opens up a lot of opportunity for innovation. So with that, Dave, take it away.
Hello, everyone. This is Dave Kellett. I'm with Intel Corporation, and I'm going to describe work that we're doing on chiplet interfaces and open source hardware today. You can read the Intel legal information at your leisure. 56 years ago, Gordon Moore wrote, "It may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected." This was in the same paper where he articulated what's known as Moore's Law. So the chiplet idea has been developing for a long time. In the last few years, technology has reached a point where chiplets are practical solutions. In my presentation today, I'm going to talk about how chiplets are being used, just as Gordon Moore predicted. I'm going to cover what we're doing with the SHIP project that we have with the US government, and especially about AIB 2.0 and a new version we call AIBO. We're planning open source release of protocol IP to run on top of AIB for the purpose of increasing interoperability, and then I will wrap it up. Our work with chiplets so far has developed what I call the first generation chiplet accomplishments. So with chiplets, we've been able to extend Moore's Law with improved cost, performance, and power efficiency. Multiple companies are building chiplets. A recent article in Semiconductor Engineering listed 20 AIB chiplets in production or in development, coming from 7 different organizations in addition to Intel. The standardization effort that on AIB that DARPA started is enabling interoperability. And so with that base, we're now starting on some second generation concepts like security. Since we introduced AIB 1.0, the application requirements keep going up, which we're meeting with a new generation AIB 2.0. And also our experience with chiplet development shows that we need to move up the stack from the PHY to protocols to help develop greater interoperability. You may have heard last fall that Intel was awarded the second phase of the state-of-the-art heterogeneous integration prototype program called SHIP. The project is enabling the US government to access the state-of-the-art packaging capabilities at Intel. Much of the effort with SHIP is about opening up Intel's advanced packaging and manufacturing. My part is about chiplet security, interface standards, and protocols. Today, I'm going to focus on interface standards and protocols. I'm giving a talk this week at a government technology conference called GOMAC Tech, where I'll emphasize the security aspect of our SHIP project. Early this year, the US government released a request for designs as part of their RAMP project. The RAMP project has 2 key areas of direct relevance to our chiplet work. The US government is asking the defense industrial base to submit proposals for designs including chiplets. The idea is that if you're selected, the government will pay you for your development. The first area to note is that the design parameters for the US government's request for proposals call out AIB as the interface standard. The second area to highlight is that the design proposals should coordinate with the SHIP program. And the reason for this is the US government is recognizing that AIB is the de facto standard for chiplets. Last fall at our CHIPS Alliance workshop, I showed this slide highlighting the depth of our AIB chiplet portfolio, covering FPGAs, SerDes chiplets, research chiplets, Intel development, other companies' developments, and universities. Today, I can add the chiplet I'm developing in SHIP with a defense industrial base partner to this list, plus the chiplet or chiplets that'll come out of the RAMP program. One thing I've realized while working in this area is that having an FPGA as an anchor device for a chiplet to talk to means you can develop chiplets one at a time. Without this, you'd have to develop 2 chiplets just to have a partner to talk to. I mentioned the project that I'm doing as part of SHIP earlier. Our goal with the SHIP chiplet design project is to develop standards, protocol, and security IP to help chiplet developers build chiplets. Now, my group inside Intel is perfectly suited for this, given the work we did on chiplets going back to Altera days with the first Stratix 10 device and continuing now with the US government research projects. I just want to add that experience is a tricky thing. Some people with experience tend to overvalue it. I had a supervisor tell me that my experience was a negative attribute, but what I found is The experience does for me is allows me to move faster since I don't have to go down any dead ends. Now, our project with SHIP covers chiplet interface standards and protocols, security, and a hardware proof of concept so we can prove out the technology in silicon. Last August, AIB 2.0 was introduced by Intel that improves performance on several axes. So the bandwidth per wire goes up to 6.4 gigabits per second. And as advanced packaging technology progresses, we get to utilize the smaller microbump pitches. The net result of this is that we can hit over 7 terabits per second per interface, even at a relaxed 4 gigabits per second per wire. Now, with all this bandwidth, we need to be concerned about power. This is addressed by using low swing drivers to get a target energy per bit of half a picojoule. And with all the AIB silicon portfolio from Intel and other manufacturers, compatibility with AIB 1.0 is a must-have. Now, at the same time, we're adding new features. Data bus inversion is a technique that comes from DRAM applications. It reduces the load on the power distribution network since you can have at most 50% of your outputs changing state. We've expanded testability with loopback modes, added an extension with PRBS pattern generation and checking. We've been able to simplify the signal list and added flexible gearboxing since we have a range of maximum frequencies that chiplets run at internally. Now, as Michael mentioned earlier, in February, the CHIPS Alliance approved AIB 2.0 as a CHIPS Alliance release specification. So we have an open spec and an open draft process. You can read the open spec at the link on the screen here. We're developing an AIB 2.0 hard macro in Intel 22FFL silicon technology with a company called Analog Blue Cheetah. And one of the first things people need to use AIB is a logic simulation model. We just posted an open source AIB 2.0 simulation model under the CHIPS Alliance GitHub repository. Today, I want to introduce a version of AIB that's optimized for standard packaging. We call it AIBO, AIB for standard organic substrate packaging. Now, AIBO is a subset of the AIB 2.0 capability using the bump spacing that standard packaging allows. Now, the reason to do this is that standard packaging substrates are more broadly available than advanced packaging. Also, you have many choices for package assembly with OSATs. 3 years ago, I gave a talk about how you might design differently when wires are free, which is almost what advanced packaging gives you. But with standard packaging, wires are definitely not free and we have to conserve. Still, I think there are applications that don't need the highest capability, and for these, standard packaging density will work just fine. With AIBO, we have the same concept of channels that we have with AIB. We just drop the number of data bits in each direction from 40 down to 10, so that the array is approximately the same area on the die as it was before. Now, since we're using standard packaging, the density drops by a factor of 4. So instead of AIB 2.0's 7.68 terabits per second, we get a quarter of that, 1.92 terabits per second. And just like AIB 2.0, the bump map is designed so that the receive and transmit talk to each other over matched trace lengths. So you can see in the diagram there. And AIBO uses TX data, RX data, and clocks with DDR transfer just like AIB. It's full duplex just like AIB. And again, with just fewer data bits per channel, that matches the density that standard packaging can provide. The CHIPS Alliance AIB Working Group has posted the draft AIBO specification as a Chapter 7 of the main AIB specification. So you can look at it, it's publicly available, the same royalty-free terms as before. And we would like to complete the spec by September. Now, the last area of chiplet design technology I'm going to talk about today is protocols for chiplets. Now, the point of our chiplet project is to ease design and chiplet interoperability. We have the standard AIB5 that I just talked about. The next area for interoperability to solve is one step up the stack, and that's the protocol level. The idea here is to build adapters to carry familiar protocols over the AIB die-to-die interface. Now, each side needs to know how the protocol is mapped to the AIB interface. So we're providing the protocol adapter pair. To users, they see the familiar protocol interfaces that people have used for years, like AXI Stream and AXI 4. And by providing the protocol IP on both sides, we make sure the mapping to the AIB PHY is understood. AXI Stream is well suited for continuous data flow, things like radio frequency ADC DAC samples or SerDes networking data. AXI 4, which we often call memory map to show we're talking about the read-write AXI protocol, is well suited for a memory controller or a memory map device. We're also building an LPIF adapter on AIB. LPIF is the logical PHY interface layer under CXL. We originally thought about using the PCI Express pipe interface, but it makes more sense to use the forward-looking LPIF interface as CXL starts to ramp up. Now, the really important part is that as part of the SHIP project, the protocol adapter code will be released as open source under our CHIPS Alliance GitHub repository. We'll use Apache 2.0 licensing, so this is freely available to anyone.
We're just under 5 minutes. Oh, perfect.
I think I'm doing fine here.
Doing great.
On my last page. So to wrap this up, we're building out an ecosystem of chiplets, IP, design tools, and services to help developers build interoperating chiplets. Our business model with open source is to promote interoperability. So if your silicon interoperates with my silicon, we together can meet a broader set of customer requirements. And I thought I'd kick off the Q&A with a question I received on Friday. And it was kind of direct. And it was, why should I use AIB over one of the other die-to-die interface ideas? And I'd say that there's 3 reasons for this. The first one is AIB is proven in silicon, it's in production. Second, we have a double-digit portfolio of AIB chiplets I showed earlier. And the last one is we're building on our open source PHY IP under CHIPS Alliance by providing the next layer up, and that is the free open source protocol adapter IP that I talked about last. So with that, Rob,
yes.
Let's see if there are any questions.
I do have one question. Thank you very much for an excellent update. I appreciate it. A question I have from the audience is, could you take a moment to explain the rationale behind the current race to make chips smaller and smaller to 7 nanometer down to 3 nanometer prototypes, while until recently 130 nanometer was all right? This has caused a rush to 1 or 2 fab facilities in the world. What is achieved by this condensation? Are there benefits in exact proportion as a 200 nanometer chip used 100 times as much electricity as a 2 nanometer chip, and it had 100 times as much latency as a 2 nanometer chip? How important is it to aim to make all processors in sub 10 nanometer architecture?
Wow. Okay. Let me see if I can
yeah, that's a lot.
Unpack some of that. The first thing is the the basis behind Moore's law was really that the increasing transistor density for the same cost is still there. It's still there's still more things that you can put on a chip than we could fit now. We'd still like to put more processors on there, more capability. But I think that what was also in that description is that the heterogeneous integration is extremely valuable, that you can mix something that does need to be super dense, like a leading edge Xeon CPU or leading edge FPGA, where there's always a desire for more, that you want to mix that with other things where density isn't necessarily the most important factor. And a couple one I'll mention is the IR photonics optical chip that they talked about at Hot Chips earlier publicly, and that uses a much more relaxed semiconductor process node than the most recent ones, because they're doing some very special IP with the photonics that is just well suited for that application, and it doesn't need to be a 7 nanometer, 5 nanometer process. So I think that the heterogeneous integration is extremely valuable, and it does have a great place to use a span of process nodes, all the way from the most recent highest density to things where there are some specialty functions or I/O that could use much more relaxed geometry.
Thank you, Dave. I just ask one final question, and if you could comment on the maturity of the design methodology required to implement what you described today with chiplets, and then also the corresponding EDA ecosystem, whether that be commercial solutions or perhaps open source.
Okay, so the maturity of the design process, the Stratix 10 powered on in 2016, and so that used AIB 1.0. It used Intel EMIB advanced packaging technology. So we've got 5 years of experience on that. There are other advanced packaging technologies such as interposers. There's a lot of interesting work being done in RDL or fan out technologies to reduce the cost of a very high density packaging. So the tool flow that we've used is standard commercial set of tools. You do have to do a link simulation between your chiplets to ensure that you can successfully signal across them. So there is some additional engineering to be done on that, but the maturity of it is well understood, and we and many other folks have done that kind of work on die-to-die interfaces.
Very good. Thank you so much for an excellent chat. I appreciate it.
Thanks, Rob.
Our next speaker is Dejan Vasilik, who is with Western Digital, and his talk is on the OmniExtend architecture and milestone updates. So Dejan.
Hello, everyone. Thanks for having me here. Today, I'll try to give you a very brief update on the state of OmniExtend and TiLink and in general coherence in the RISC-V ecosystem. And just to refresh everyone's memory, in 2018, Western Digital was faced with a dearth of high-performance interconnects that would allow us to connect very low latency, high-performing kinds of memories like magnetic RAM to the prevailing compute architectures in a data center. And it was a strategic problem for us, and faced with this rapid rise of the RISC-V ecosystem, we proposed a new format or new standard interconnect, which wasn't all that new, right? Our proposal was to try, in the spirit of the open sourceness of the RISC-V ecosystem, to also use a completely open fabric, such as Ethernet, for transporting coherence. In other words, we wanted a completely unencumbered, modern, high bandwidth, low latency bus to connect not just CPUs, like socket-to-socket buses, but also all these other kinds of devices to its storage in our case, but also GPUs, FPGAs, accelerators, and other kinds of ISAs in a way that is not asymmetric, like peripherals buses like PCI Express and CXL and so forth. So in other words, the idea would be that one CPU would not own the architecture of your data center, and you would be allowed to create a more heterogeneous architecture out of disparate components that are assembled in a way that fits the algorithm and the purpose. So this was usually called the memory-centric architecture, memory fabric, and we hasten to explain what it is and what it isn't, because most folks, when they hear memory-centric, think of a DMA-like system where you have a CPU with some cache and DRAM, and then you have a network interface card, which is a DMA engine. And then typically you have some sort of software that manages the so-called fabric. And this fabric exposes some large amount of memory that basically you have to run your local software to fetch blocks, pages, or whatever you want to call them. And then your NIC does the data transfer, and the DMA engine stuffs it in the DRAM, and then you have to load it through the cache to your compute pipeline. So this wasn't really fitting for us, and this is what started the whole project in our group in Western Digital Research in 2012, was that this little lightning bolt here represents a context switch. And we had several memory technologies in the pipeline that were actually so fast that the context switch cost was an order of magnitude faster than the cost to access memory over the fabric. And the fabrics have gotten so fast that typically a latency to fetch a block over fabric is actually lower than one context switch cost on Linux and the modern CPUs. Right? So this was out. The sort of intermediate solution that some folks played with, in particular Gen Z, was this idea that you have some sort of online translation that happens very fast, and then you go with the loads and stores into the fabric to fetch your data and store your data. So just to be clear, what we proposed was actually a full cache coherence protocol, like the protocols that go between sockets on many computer architectures today, but they would go straight into the fabric. In this case, this was Ethernet. Other contenders were InfiniBand and other high-performance fabrics. And then you basically fetch cache lines straight into your cache. So your local CPU wouldn't even have to have DRAM controller or lowest point of coherence. And this is illustrated by this PT here, which indicates page tables. So the idea was that whatever your paging mechanism that your CPU or your OS use, the page tables might be sitting on the other side of the fabric. So your whole fabric would be behaving like one single computer. Now, what we envisioned, like I said, was a completely asymmetric, a completely symmetric interconnect. And so these little noodles represent SoCs that a lot of you folks are taping out, where you have the Encore with a bunch of local facilities, and then you have a bunch of cores that talk through some sort of a local on-chip coherence bus, which in the RISC-V world was Tie-Link traditionally. And the idea was that you could connect two of these socket to socket via this OmniExtend Ethernet fabric. Or you could connect one of these to a peripheral that would contain, for instance, a non-volatile memory, a high-performing memory that would appear as a lowest point of coherence. And as basically you plug this into your SoC, and the SoC would just see DRAM or something that looks like DRAM, right? But more to the point, what we wanted to achieve with these new generation of smart switches was to try to get the switch to behave like an endpoint for coherence protocol, and then allow you to extend these systems either by plugging a lot more sockets together, like thousands or tens of thousands of sockets, or to have completely free design systems where you have a large amount of memory and a few sockets, or have a large amount of sockets with a little bit of memory, and then attach machine learning accelerators, FPGAs, other kinds of compute. So to bring you up to speed, we published a protocol called OmniExtend. There was a version 0.1 that was shown off in December 2018 at a trade show. And it was based on Tie-Link 1.7. Since we've actually fixed some bugs in Tie-Link in collaboration with Sci5, and Tie-Link 1.81, I believe, is the current version that's available under Creative Commons license online. And this is transported over OmniExtend version 1.03, which is also under Creative Commons license on GitHub. So by now, this is actually a mature protocol. We've had it running in the lab for a little over a year and a half, I think, and it's had uptimes of many months with up to 4 sockets. I'll show you some performance numbers in the next slide. I want to point out that we started out with a protocol that was relying on these custom switches that will allow you to reprogram the Ethernet header for better performance and so on. But since there have been some mergers and movements in the industry, and we've decided to revert back to a Ethernet L2 compliant header. So you can use any switch, any off-the-shelf switch, like a Broadcom switch, or even these very inexpensive switches you can get off Amazon for $100. The protocol has changed to incorporate multiple messages per frame. So it's a fairly high performance, high bandwidth utilization protocol. It has retransmission capabilities. So it handles lossy fabrics like Ethernet gracefully. And the current binary that you can download for VCO 118 off of GitHub actually has multiple Tie-Link serializers, so it can handle socket to socket for up to 4 sockets through a switch, or you can go to a smart switch and then extend the system to a lot more sockets. So just to point out again, you can download this for VCO 118. It runs very stably in the lab, and it's an FPGA implementation at 100 megahertz. It's a Sci5 U5 RISC-V core that was based off of the rocket chip developments. All right, these are some performance numbers. Keep in mind this is FPGA, so this is very high latency in general because the clock rate is very low. As you can see, we've been running a single node with local DRAM, 2 nodes with direct connection or connection through a switch, and then up to 4 nodes with a local remote DRAM. And you see, L1, L2, and L3 cache cache's work is designed, right? And then you go to these latencies on the order of 5 microseconds for systems that can extend pretty much to through one switch to about 64 or 256 sockets. These are just your standard NUMA systems running a single instance of Linux, and you see here 16 sockets visible, and you can run pretty much all the standard software as if it was a single computer. All right, so I wanted to use the rest of the time to bring you up to date on the developments with this OmniExtend, and also on the discussions for the future of TiLink and discussions of the future OmniExtend. So the first thing that is going to be interesting to those of you folks who are hoping to attach accelerators to OmniExtend enabled SoCs is that we have developed a lowest coherence RTL that is going to be fully open sourced. This is at the moment is based on a standard board from Xilinx Alveo I believe U50. It's an HBM board with 8 gigabytes of HBM. And you will be able to run a storage device simulation that storage device which it attaches directly to OmniExtend. So it essentially shows up as a lowest coherence, and you simply get a memory region that is at this time backed by HBM. But this RTL is going, like I said, going to be fully open sourced, and you will be able to run simulations of different kinds of future memory technologies by simply slowing down the memory or introducing algorithms to capture the idiosyncrasies of memory, such as flash, magnetic RAM, resistive RAM, and so on. The other thing that we're working on hard is what we call Beyond Intel architectures, with apologies to our co-competitor. So these are things that you cannot do with current off-the-shelf hardware, right? So one of the things that's been generally difficult to achieve with non-exotic hardware is more than 4 sockets. In the RISC-V world, off-the-shelf RISC-V world so far, there aren't really multiple sockets, so OmniExtend is your only game in town if you want to play with scale out the RISC-V. But we're hoping to show pretty soon systems with up to 64 sockets of one switch, and then there are efforts to understand the capabilities of these smart switches to have the switch terminate the protocol and then have multi-switch systems that enable scale out to, in principle, unlimited number of sockets. In practice, it's limited by financing, right? And then another thing that is happening, so I briefly mentioned we have a boot protocol defined now that's defined online on GitHub. So the boot protocol allows you to configure the endpoints to behave as any kind of identity, right? So you can have systems where you have a one OS see all the boards as one coherent whole, or you can have a system where each board boots an independent OS and they all see a global shared memory region in addition to their local coherent memory. So I think the thrust of the scale out efforts at the moment is on these independent OS systems at the moment. Simply because the changes required to, say, Linux kernel and the infrastructure and the software infrastructure, right? The signaling to the user process of failures and fault tolerance and so on are fairly daunting, right? So we will probably start out with independent OSs that handle or try to handle gracefully, loss of individual boards, and then progress from there to changes to an upstreaming of changing to kernel to handle fault-tolerant coherence itself. Right? Finally, we have again a project with a QEMU, right, that emulates the entire coherence endpoint, which you can download. It is based off of the P4 QEMU emulations that were available in the networking world. And so the hope is to publish pretty soon a version of this that interfaces with hardware. So in other words, you'll be able to have a system for development of your own custom coherence protocols or endpoints where you can have an actual hardware endpoint, right now the FPGA, and in the future an SoC in silicon, and connect it with an actual software endpoint, and these will behave like a single hardware computer. And finally, there's some look into other architectures, non-RISC-V ICs, compute accelerators, like machine learning accelerators, and attaching them to these coherent attach. I just wanted to briefly mention the discussions that have commenced about the 2.0, what we call 2.0. So a lot of folks have complaints about TiLink, that it doesn't perform, or it doesn't do this, or doesn't do that. Some of those complaints are well-founded. And there have been discussions among us here in Western Digital Research and with Sci5 and with many other groups of what this should look like going forward in the future. So I just wanted to point out that the current focus of us in Western Digital Research is actually on scale out and fault tolerance, right? So it's not necessarily, we're not necessarily looking at raw benchmark performance of multi-socket systems in RISC-V. We think there are a lot of you who are interested in this, and there are probably going to be some developments here. We're a peripherals company, and our main interest was in having a high performance attached for storage devices, which doesn't really care about the forwarding protocols, 3-hop protocols, 2-hop protocols, and so on. But we would like to be able to offer you, say, a system with 1 exabyte of main memory. So our main thrust of these efforts is basically on having many storage devices attached to a single coherent domain, and then fault tolerance when they wear out, when they fail, when somebody unplugs the cable, and so on. So that's why we're kind of focusing on the independent OS model right now and on figuring out to communicate node loss to user processes, so you don't have to bring the whole cluster down when one device fails or wears out. And so I think I'm just about out of time, so I should stop here and see if there are any questions. Thank you.
Thank you so much, Dejan. So very good talk. I appreciate it. One question I just had from my side, which was in terms of architectural modeling with OmniExtend, is there any capability of being able to model 2 different pieces of CPU or accelerators together, or how is that done, or any comments you might have?
Right, so there is a gap in modeling from software to the entire system, right? Now, this is a fairly daunting task, I should point out, right?
Yes.
To model the entire CPU pipeline, the entire behavior, all the caches in the system, the serialization, the quirks of the fabric, and then the behavior of the whole system. So we're not quite there yet, right? We're making strides piece by piece. And one thing that was sorely missing was the network part. And this is where we made the biggest strides. And this is the QEMU framework for emulating the actual protocol communication and so on. So there's this whole framework for emulating P4 switches, right? And for emulating loss of packets and so on. And you have an entire software switch that's available for free. And it's completely open source. And we've leveraged this to introduce coherence endpoint emulation on this. And I'm not sure if the entire thing is open source, but we're planning to open source all this stuff. It's built on open source infrastructure. So you will be able to basically take a frozen trace of coherence commands coming out of your pipeline or out of your last level cache, and just introduce them into this network simulation system, and then introduce packet loss and see what happens. Right? Now, the question was, can you get from software to there? So this is a much more difficult problem where you sort of need to simulate the entire cache hierarchy. We don't really have much to offer in that. Like, there are many of you who have much more elaborate infrastructure for simulating caches and state machines and so on. So the tying in of these two sets of hierarchies of simulators is not quite there yet. But of course, we invite everybody to join the fray and help us hook this up together.
Appreciate that. So I have one question from the audience, and it is this. I read something about OmniExtend with RISC-V doing a unified memory standard. What is the status of that?
So let me try to parse this unified memory standard. Right, the word memory is perhaps overloaded, right? So we will have, we're proposing a unified coherence protocol standard, right? Now, coherence protocol is an overloaded term, right? So it contains commands, or rather transaction types that include memory access and also the non-memory access, right? So there are MMIO transactions and coherent transactions, and MMIO is everything that's non-coherent, including access to other sockets, interrupt controllers and so forth. So in that sense, OmniExtend is already a standard. It is given to the world as a Creative Commons standard. And I think we're in the process of formally recognizing a standard in CHIPS Alliance workgroup. Right? So that is the status of that, I guess. I'm not sure, is that the answer to the question, or was the question?
I believe it is, yes.
Yes.
Thank you for doing that. So, and that concludes the time we have. So thank you, Dejan, for your update. I really appreciate it. So our next speaker is Jack Koenig from Sci-Fi, and he is going to discuss Chisel advances for next generation SoC designs. So Jack.
Hello. I think there we go.
Yes, we can hear you and see the presentation.
Okay, cool. I should click to start. All right, I should be able to control now. Excellent. Okay, so let me start my timer. All right. Hi, everyone. My name is Jack Koenig. I am a staff engineer at Sci-Fi, and I am, you can see the nice little double acronym there. I am a member of the Chisel Working Group Technical Advisory Committee. So in our as a CHIPS Alliance project, we have a technical advisory committee to run Chisel and related projects. And so I'm going to talk a bit about those projects. So, you know, kind of letting you know what I'm going to talk about. I'm going to introduce what Chisel is and related projects. I know you heard a little bit from Professor Nikolic and from Michael previously, but I'll talk a bit about that as well. I'll provide some highlights from the last 6 months since the last CHIPS Alliance workshop, and I'll talk a bit about what we're doing going forward, what to look forward to. So first of all, like, what is the Chisel Working Group? Well, the first question there is, what is Chisel? And as you heard earlier during the Chipyard talk, Chisel stands for Constructing Hardware in a Scala Embedded Language. It's a domain-specific language where the domain is digital design. That's a lot of words, but you know, Verilog is a domain-specific language where the domain is digital design, and Chisel is as well. Chisel just differs in that rather than being a standalone language, it's actually embedded in another language. It's embedded in Scala, which is a general-purpose programming language. As Professor Nikolic mentioned, it is not high-level synthesis, nor is it behavioral synthesis. What it really is you're writing a Scala program where you construct hardware objects and build your hardware design that way. We like doing this in Scala because Scala provides modern programming language to things like parameterized types, object-oriented programming, functional programming, and static typing. All these features are things that we think help you write, you know, reusable and maintainable code. And it's intended for writing reusable hardware generators like Chipyard and all of the projects, related projects mentioned in there, as well as, you know, others. So, you know, kind of to give a brief overview of what Chisel really is, there's no loss of expressibility so long as you're writing, you know, synchronous digital designs. So this is a moving average FIR filter that looks pretty similar to what you might write in Verilog. You have some inputs, you have some registers, you have some arithmetic, right? But the question comes when you want parameterization. So here we have a parameterized bit width, just like you would do in Verilog. But what if you want more than 3 points in your filter? What if you want weighted averages? And so what you really want to be able to do is write a generic filter, not just one specific filter, but maybe a whole family of filters. And so Chisel makes it really easy to write a parameterized FIR filter. So I'm not going to dwell on this code here. Please check out the Chisel Bootcamp if you want to really understand it. But you write something that kind of looks software-y, but in reality, you're just manipulating the exact hardware constructs you want. There's no synthesis going on here. You are in control of every flop and every, you know, logical thing you want to do. And so this is parameterized both by the bit width and by the coefficients, not only what those coefficients are, but how many of them there are, which affects, how much in the time domain you're stretching your filter. And, this is metaprogramming where you're writing a program that is then constructing another quote program. Now that second program is the hardware itself. So not quite the same, but you're really reasoning about constructing hardware when you do this. And so using this generic filter, we're able to create that same moving average filter just by parameterizing this one. We're able to create, other types of filters, a simple one cycle delay filter, or perhaps a triangular filter with 5 points. The point is that we wrote this one filter and now we can do all these different things. And so that's really what Chisel is about. That's what Chipyard is built on. That's what Sci-Fi uses in a lot of our technology. So this is really what Chisel is about. So I mentioned previously that Chisel is about writing reusable generators, but as anyone who's done any hardware design knows, that's really difficult, right? As soon as you have some specific platform, you end up doing platform specific changes. If you're doing something in IBM 45 versus ST28 or a more modern technology, you end up needing to do SRAM macros or other very specialized things in your physical design. Similarly, FPGAs have a whole host of other features. And so it really breaks reusability when you're if you try to write something that's reusable, but when you have to leak in, platform specific stuff. So in order to specialize our designs for different platforms, we realized we needed a a hardware stack similar to what you have in software, right? When you write C++, you don't care if you're writing it for, for x86 or ARM or RISC-V. And we want the same thing in hardware. So what we did is we took Chisel 2 was pretty monolithic, and we replaced that with Chisel 3, which is Chisel as a language, really just kind of this front end along with the Fertile compiler underneath it. Now, this is a gross simplification because I'm kind of leaving out a lot of details about what goes on underneath since we just emit Verilog. So I want to give a shout out to all the other projects that do the real heavy lifting here, especially OpenRoad, Verilator, and OpenFPGA. So, Fertile, which is, the other one of the other big projects in the Chisel working group is, it's a compiler that allows you to, let me see, I should be able to use a pointer. So it has, kind of your design as an abstract syntax tree with core transformations that lower it to Verilog, or does do other specializations. But what's really critical is it allows you to insert custom transformations to specialize the flow. So this is really important in Chipyard and in FireSim and at Sci5 as well. There's a lot of different customizations that you may want to do based on your own custom flow, your physical design, or just what technology you're targeting. So that's handled, a lot of that's handled by the robust metadata and annotation support, which is really critical for that extra collateral for physical designer verification. And so there are several projects in the Chisel working group. I really talked about Chisel and Fertile, but there's a few others, in particular Chisel Test, which is our testing framework to write unit tests, and Treadle, which is our emulator for Fertile, or simulator for Fertile. But there's several others, and I'll just note that we're currently a Chips Alliance sandbox project, which is like the first step of that Chipyard, of the Chips Alliance life cycle of projects, but we intend to graduate in the near future. Okay, so now I'll talk a bit about what's been going on over the last 6 months. So if you want to see what happened in the year before that, please check out my previous talk, which was part of the workshop on YouTube. The previous Chips Alliance workshop. So first of all, we actually moved the projects over to Chips Alliance GitHub, so you can find them there. There's still a couple more to move, but at least the major ones are moved over. We've been further improving our website, which is important for documentation. So we have the API docs for more advanced users to see everything that's available. We have more project-specific documentation. That Chisel link is especially useful. There's a lot of documentation there. We have a community page where you can see all the cool stuff that's going on and find links to our Stack Overflow or Gitter where people chat. And we now have a search bar, which is very exciting. It's not quite Google, but at least if you know the keyword you're looking for, you can probably find the page that talks about what you want. One of the things I'm most excited about on the website is our documentation examples are actually compiled and run. So historically, documentation gets out of date, but now we are always making sure that our examples run against the most recent version, which is very exciting. So in the last 6 months, we've had a few more releases, which you can see there on the right. One thing I'm really proud of is that we have a robust backporting methodology for bug fixes, such that even though we're currently on 3.4.2 and about to release 3.4.3, we still, as you can see, release bug fixes for 3.2 and 3.3. And that allows people who may be stuck on older versions to keep getting important bug fixes. And we are also publishing snapshots of all the stable branches and the unstable branch, actually. So for people who want to try the bleeding edge, it's pretty easy to do now. This is from last time, so I'm going to go through it pretty quickly, but starting in Chisel 3.4, we did a lot of work on improving naming. So, you're writing a program to generate hardware, so you can, of course, call functions. And so in this case, it used to be we were not very good at naming these signals, but now we actually can name, X and Y, as well as we give them a prefix from the result value that they're returned to. And this is really important because you could call this function multiple times from multiple places. So it allows you to kind of scope the signals that are created based on your actual call stack. And you have some control over that. But what I want to really get into is in the last 6 months, we kind of refined this naming. So this example is a little specific. So it may work well for people who are more familiar with Chisel and maybe not so well for others, but I'll just try. So say you have some module with some optional tap. And let's just say this tap is for debugging a signal. So based on a parameter that may or may not exist, an option is just something that may be set or may not be. You'll provide a width, and if the width is set, then we'll create a port. So the question is, what should the name of this port be? And this is actually a pretty subtle question. And one option is port, because when you construct the port, that's the value you assign it to. One option is tap port, because as I talked about, we have this prefixing, right? And so port is scoped inside the tap value. Another option is tap, because you actually, in Scala, the last expression is the return value. You return the port to tap. And so this top level tap value is the port, or it could be tap port because later we have another value that refers to the same port. And so what is the name that you want? In 3.4.0, when we first introduced this, it was getting tap port, which is, it turned out not what our users want. What they really want is tap. And so there's a lot of detail and subtlety in how this works, but I'm pretty proud of the point we've come to. And I think the strategy we use for naming here is a pretty good one across the board. And we've been using it for 5 months, and people are finally deleting all their little .suggest names, which is how you can try and add more control to the naming in Chisel. But people are finding that the default names are working really well for them now. Just other shout outs, to recent tape outs. A lot of times, you kind of want to say the proof is in the pudding. On the Google Skywater eFabless shuttle that Tim will talk about later, there were at least 3 designs, including Chisel, which I have the GDS plots for. Berkeley, this tape out was a little while ago, but they just recently presented it at ISSCC, which is a pretty beefy core here with 8 tiles, 4 L2 caches, an L3 cache, lots of SerDes. This is a real chip where basically everything in the middle here is implemented with Chisel. And then, for my own company, Sci5, our recent board, the Hi5 Unmatched, most of our design is in Chisel. So, we have these pretty quick dual issue network cores, memory hierarchy, a lot of stuff going on there, all implemented in Chisel. And there are others that if I missed any, please let me know. And there are others that I wish I could talk about but can't. But just letting you know that there's a lot going on in real silicon. So now I have about
5 minutes, by the way.
5 minutes, perfect. So I'll talk a bit about what we're working on and what's coming. So historically, Chisel's been used primarily for ASICs, as I just kind of showed, but that means it's been difficult to take advantage of a lot of FPGA-only features. And for all of you who kind of work in that open source FPGA realm, that's been very frustrating. So there's been some recent work on this to improve our support out of the box for FPGAs, and we'll have a new option, --target FPGA, to help with that. I mentioned the next version is 3.4.3, so this will not make that boat, but should make the next minor version. So I just wanted to let you know that that's coming. This is very much more in the weeds, but my Chisel users will probably recognize what I'm talking about here and be happy. So clone type is just this implementation detail that leaks into the user API, and that's never a good thing, right? You don't want implementation stuff. And when I say implementation detail, I don't mean physical design. I mean implementation of Chisel itself. So this has just been a huge wart in the language for a long time. We had auto clone type 1, as you can guess by there being number 2. But it had 3 important limitations. It required you to do some boilerplate. It worked in most cases, but not all. And importantly, it was actually quite slow. You wouldn't notice this for most designs, but when you're starting to get to large, mini tile SoC, it really starts to add up. And so now in the next version of Chisel in 3.4.3, the Chisel will be able to do this much better. And I'm very excited about this feature. Another feature that's a little more half-baked, but it's something we're working on, is what we're calling data view. So often when designing hardware, you may have some hardware value that you wish you could reason about or manipulate as if it were a different type. So a canonical example of this is an AXI style flat bus interface, which is fine. And that's like kind of what the standard is. But a lot of times you'd like to manipulate it as if it had more structure, right? The ready and valid things are at the same level as your payload, and it's just kind of hard to deal with sometimes. And so people would like to be able to manipulate it using more structured typing. And then another example, sometimes you may have a 1D array of registers and you'd like to treat them as if they were 2-dimensional. And so this is kind of similar to a union in System Verilog, and people use that for similar things, but there's a lot of use cases that aren't handled by that, where sometimes the raw bits mapping may not correspond 1-to-1, and there are other limitations as well that will be described more in documentation for this feature once it's done. This is also similar to a facade pattern in object-oriented programming, but that's very boilerplate heavy. It's similar to conversions in functional programming, but those don't allow you to manipulate the underlying representation. And so the reason we came up with the name data view is the best analogy is a view in SQL. So for any database people out there, this is very similar to that. And so this is a really powerful feature that I think is going to enable a lot of design patterns that I think people will really like. It's a work in progress, but I look forward to this in Chisel 3.5. I want to also note that there will be a Chisel Community Conference in Shanghai on June 25th. So I made this slide, I submitted my slides before I got the update. It will be June 25th, not the 26th, just the 25th. It'll be co-located with the RISC-V Summit. So keep an eye on our websites, which I'll include another link to later. and maybe put in the chat for the details about submissions and more details. So kind of what else is going on. I talked last time a bit about verification, and I'm only glossing over it this time, mainly because a lot of this work, people are worried about, pre-publication rules, but I can tell you that there's a decent amount of work going on, and I'm very excited for what students are doing. There's, all these things I mentioned here. There's works on how you specify and run your formal verification. There's constrained random stimulus generation, and there's software-based VIPs that people are working on. So there's a lot going on, but I can't go into too much detail at the moment. We continue to work on documentation. For my Chisel users, we are working on support for the next version of Scala. That's almost done. And then other just minor things like vector literals and better connection semantics that I'll just leave for future PRs and documentation. So that's it. Please get involved. Go to our website, chiseling.org. You can find a community page with links to all kinds of places, previous talks, Gitter, ask questions with Stack Overflow. Thanks a lot.
Thank you so much, Jack. That was a great talk. And we have 2 questions, so I will share those now. First question, was there a specific reason for choosing Scala as opposed to other common languages as the one to embed the HDL into?
Yes, so I will say that predates my time. I joined, I started as a grad student at Berkeley in 2014, and I think Chisel was created in 2010. But I can say that Scala has a lot of support for DSLs for embedded DSLs. A lot of attributes of Scala make it easier to embed a language. That was one of the design goals of Scala. It's also a modern programming language. It has functional programming is getting more and more popular, and Scala was, it's not on the forefront of functional programming, but certainly on the forefront of trying to make it popular by making it run well on the JVM and stuff. So those are some of the reasons. I know that the original Chisel work was actually in Ruby, and there were performance problems. And so Chisel being a compiled language runs a lot faster than that, or Scala being a compiled language runs faster. And there's other benefits that I'm happy to talk about. If you want more details, please come chat on Gitter or in the chat here.
Thank you. The next question I have is Chisel construct hardware. Are you guys adding support of verification in Chisel so that design and verification can go hand in hand with the same language? What is the time frame that this might be available?
Right. So Professor Nikolic mentioned that in Chisel 3.4 we added system Verilog, assert, assume, and cover style constructs. So those are at least basic primitives by which you can build a lot of things. We also have Chisel test, which is kind of a Scala bindings to run your tests, kind of similar to what you might write in System Verilog. So those are 2 things that the timeframes that they exist now. There's always more work to be done, and so I don't have specific timeframes for like the constrained random stimulus generation or better formal support, but I can say that they're actively being developed. And if you're interested, I can put you in contact with the people who are doing the heavy lifting of that work. If you can reach out to me on Gitter or in the chat.
Great. Well, thank you again, Jack, so much for your presentation. I really appreciate it.
Thank you.
All right. Our next presentation is Zdenek Prickle from Codasip, and he's going to talk about the Codasip Swerf core support package in a nutshell.
Hi, everyone. I hope that you hear me well.
Yes.
Yeah, okay. So let me start. Today I'm going to talk about who we are, what we do, and then we will focus on one particular product, which is we call it Swerf core support package. So as a company, we were founded in 2014 in the Czech Republic. And we are basically focusing on the RISC-V processor IPs, plus the EDA tool by which you can customize the tools. It was the original like a business model or product that we had. And recently we added also the Swerf core support package that nicely complement these 2 items. The EDA technology itself, the tools that we are using for customization, these tools were developed at the university here in Brno in the Czech Republic. back a long time ago. Actually, we are founding members of RISC-V Foundation, or international nowadays. And we actually introduced the first licensable RISC-V IP back in November 2015. As far as we know, we were the first one. The company itself, the R&D centers are located in the EU. So we have a office in Brno, which is the biggest one, but then also in France or UK. So all in all, more than 90 plus employees, and we have a presence around the world, including China, of course, Japan, North America, and so on. If you look at the product that we have, let's split it into three parts. The first, we have our own RISC-V processors that are designed in-house. They are meant for the embedded low power design through the high performance embedded up to Linux capable cores, plus multi-core solutions as well. So these are the CPUs that were developed by us, and they are developed using our methodology that builds on top of CodaSIP Studio, which is the second product, where the CodaSIP Studio is the EDA tool that I was talking a while ago. So this is a EDA tool by which you can really, create pretty much any CPU from scratch. We did a RISC-V in this case, and then you can customize the processor in any way as a customer. So it means that, for instance, if you need some secret sauce that you would like to eat inside of the CPU, or if you have some kind of key differentiation point, then you can add it there thanks to the methodology. And the methodology itself comes with the full flows, which means the design, as well as verification, as well as SDK, as well as debugging. Pretty much everything is auto-generated for you using a studio. So you get the RTL, you get verification, a suite that you can run and operate. You get stimuli, either fixed one or randomized one. You get the SDK, including compiler that's aware of your changes, and many more. So this is the second product, which is called CodaSIP Studio, and the last product that I like to focus today is a CodaSIP Swerf Core Sapro package. So what this actually is, well, it's the whole environment. It's not necessarily package itself. It's like an environment for integration or deployment of the Swerf Core CPUs, and I will talk about what they are in a minute. So if you look or focus on the third item, which is the Swerf Core Sapro package, so let me start with a short introduction of Swerf itself. So what the Swerf actually is. So it's an implementation of RISC-V spec, and originally we had Swerf EH1. The EH1 was developed by the Western Digital, and it was open sourced via Chip Alliance. Later on, the Western Digital released also the two more cores. So it is EH2, that's kind of successor of EH1, and then also EL2. Now, if we look at the feature set of these cores, then if you start with the EH1, which is the first one that was introduced, then it's a single-threaded dual-issue implementation, really high embedded core, high performance embedded core, really nice one. You can configure it in many ways. You can configure simple things like the branch prediction through the number of pipeline stages. You can configure many things, and everything is available at the Chip Alliance for you. In the case of EH2, they added a second thread, so the performance is really nice one in this case, because you can have a real multi-threading in the CPU, and I think it was the first of a kind in the RISC-V domain. Well, then if you need something on the lower end, if you just need some housekeeping CPU or something like that, then you can choose from the EL2, which is single-threaded again, and as you can see, it is just a 4-stage pipeline. And the main focus for this core was really to have a really nice low-power embedded CPU. So again, all of them are available through the Chip Alliance, which is good. But then, you have RTL. But the question is whether it's actually, all you need, or whether, you need more than that. Because if you take the RTL, that's fine, but you need to have also other tools or other frameworks, such as the compilation or SDK that's compatible with the RTL. You have to have a debug infrastructure as well, so you can debug properly on the CPU. You should have some kind of comprehensive documentation that helps with the integration of the CPU and so on. Then there is a question about the support. So if you as a customer, you would like to create a real chip out of this one, what if there is a bug in it? So, who are you going to call? Western Digital or community or who? Then if you do some kind of synthesis, then you may end up with some troubles there as well, because the synthesis script is not open source and you have to write it. So, what if you do a mistake there? Then, again, who are you going to call? And then similarly to other parts like, the RTL simulation, although there is support for Verilog, but what if you need to have a support for the commercial grade RTL simulators and so on. So as you can see, the RTL is really essential, that's true, but it's not enough. I mean, you usually need more than that. You need to collect more information, you need to collect more tools, more data to be able to integrate the CPU and program the CPU later on in the real design. And it was actually this question, or these questions were actually a kind of kickoff for our Sabro package, because we said, okay, let's create a package or an environment in which you can actually get pretty much all you need at one place, then you can start with. So on your side, you don't have to care of which version is compatible with which, in the case of, compilation and simulation and the RTL. So this is done on our side for you. And then all you need to focus on is really on the real job, which is integration of the CPU, or maybe writing a software on top of that. So we created the Swerf core Sabro package, and there are two main versions. One is free version that's available on GitHub, again through the Chip Alliance repositories. It's a free of charge. It's for students or educational purposes, and it contains a lot of stuff already, including the whole compilation toolchain, including the RTL for the CPU itself, but also for the SoC. So there is a Swerf SoC that integrates the Swerf cores. Originally, it was done for EH1. We enhanced the Swerf or patched the Swerf, so we have a version that is able to talk with EH2 as well as EL2. And you can use these Swerfs with the open source compilation toolchain based on the GCC to run, for instance, benchmarks to get really nice benchmark numbers out of the Swerf and reproduce some of the nice benchmarks using correct tools. There is a bunch of documentation, so it's done in a way that you basically download the Docker image that contains pretty much everything. It contains the free and open source packages that you can look at. Each package comes with the documentation that shows how to use it. So for instance, there is a documentation that relates to the benchmarking. There is a documentation that relates to the IDE for the software development and how you can create projects or C project really easily in it, because then Swerf Sabro package preset pretty much everything for you in terms of software development. There is also automation for the debugging, so then you can use the proper version of the OpenOCD with the CPUs. So then you can do also the on-chip debugging either under real silicon if you have it, or on the FPGA. So that's what I have mentioned. Everything is prepared for you guys, and that's part of the free version. But we have also the Pro version. Now the Pro version comes with additional stuff in it, and basically, if you look at the content, then you can find out that there is a set of EDA scripts that you cannot really easily open source. So there is a flow, complete flow for commercial grade EDA tools from guys like Cadence or Synopsys. So then you can just really simply integrate or install this commercial grade package inside of the environment, and then you get pretty much all scripts you need to run the synthesis flow. There are also other parts like verification or advanced verification flow, including verification environment for Swerf. So then if you need, or if you would like to do some kind of modifications, then we may help you with that because we have verification suite on top of that. There is some other feature sets that you can check on the GitHub to find out what's in it. Last but not least, what's important is that with the Pro version, we offer professional support, which means that you can have an account where you can ask questions related to the Swerf in general. So it can be on the integration side, it can be on the feature set, it can be on the customization even. So this comes with the Pro version. That's again the commercial grade version of a Swerf core support package. Speaking of the commercial grade features or offering, we actually created some add-ons right now to the Swerf Core EH1. So the add-ons basically brings more functionality in it, and namely it's a high performance floating point unit, and it's a single and double precision. So it follows the RISC-V FND extensions. So then you can have the Swerf EH1 in a configuration with it, and the benchmark numbers are quite nice with the high performance FPU. Then we also noticed that quite a few customers or prospects that we were talking to, they were missing a data cache. So this is something that we also fixed or added on top of EH1. So now the data cache is there as well. And you can configure it similarly to the instruction cache, which means that you can configure the interface, you can configure certain features of the data cache, such as size, number of ways, cache line, these kind of things that you can expect that are configurable. That's part of the add-on or add-ons as well. Last but not least is that we integrated the ZBB extension for the bit manipulation. So as you may know, so EH2 or EL2 comes with some bit manipulation instructions already. And I think that the final bump or the latest update at the Chip Alliance with regards to EL2 comes with quite a few actually bit manipulation instructions. It's kind of missing in the original EH1. So this is the reason why we decided to integrate it as well. And the selection of instructions were based on the, again, customer engagements that we had. And so we tried to select just the set that basically was asked the most for EH1. So then you can ask for all-in-ones package where you can have pretty much everything, but you can also pick and choose. So for instance, if you need just the floating point unit, then we can do it. We can really do it for you without an issue. So it was really high-level view or description of what we have in terms of Swerf core support package. So to summarize it, again, there is a open source version that feel free to check it on the Chip Alliance GitHub. It has pretty much everything that you need for get up and running, including the software stack. You can just enjoy the feature set that it comes with, because again, it's not just a simple package. It's basically an environment with many packages in it based on the Docker. And if you need more than that, if you are really serious in the case of the integration and you think that you need support, for instance, or you need some additional add-ons like, I don't know, FPU, then you can move to the Pro version, where we are more than happy to give you more support in this case.
Thank you, Zdenek. I did have one question. Do you anticipate, I don't know if you can comment on this, about providing support for different open source implementation tools at some point, such as our next presenter will be talking about, or perhaps as Professor Nikolic spoke of earlier today?
Well, the support that we are providing covers the core itself, plus also the tools. So, for instance, we did a lot of improvements in the case of OpenOCD to make it up and running for EH1 as well as other CPUs like EH2 and EL2. So we are supporting also these projects as well and actively donating back what we found.
Very good, thank you. Well, thank you again for your presentation. I really appreciate your preparing it and coming today to share with us.
Yeah, my pleasure.
Thank you. Our next presenters will be giving an introduction to the Open Road project. So it gives my pleasure to introduce Professor Andrew Kong from University of California at San Diego, and also Tom Sparrow of Precision Innovations, who both come to share the development of Open Road and the progress that they have made. So Professor Kong?
Yes, can you hear me?
Yes, and we can see the presentation as well.
Great. Okay, so hello everyone. My name is Andrew from UC San Diego, and Tom Spyru and I are extremely excited to give this update on the Open Road project. Open Road delivers an open source RTL to GDS EDA system as part of the DARPA IDEA program. And there's a lot of friends and supporters of Open Road that we can see in this meeting. So we'd like to start out by saying thank you from the entire team. And this is the Open Road team. Tom has been the chief architect and technical project manager of Open Road since July 2019. I serve as the PI of the project. And some new faces in the past year include Professor Larry Clark and Dr. Don McMillan, who's a very well-known logic synthesis expert. And here is our project website. Our goal is to deliver open source, 24-hour, no human in the loop, tape out clean, RTL to GDS in advanced Foundry nodes. And this requires a modern EDA tool architecture, a shared hierarchical database, engine integrations to support tight incremental optimization, unified executable, easy to use, Tcl or Python scripting, and a lot more. So Open Road's scope includes all of digital layout generation as shown here from the IDEA program's original definition in DARPA's broad agency announcement, as it's called. In the past year, we've taken on the database task of the IDEA digital flow, including advanced node support, left 5.8 and more. And Arizona State's ASAP project is a new base technology task in Open Road. We completed an extended set of phase 1 deliveries this past fall. We demonstrated capability to automatically generate tape-out clean GDS in GlobalFoundries 12LP and TSMC 65LP. So at the right is a GF12 single-core Black Parrot SoC in University of Washington's pad frame. Our database has seen a lot of improvement. That ASAP 7 research PDK was open sourced in mid-December. We've added to the team, released an extraction tool, and turned our focus to PPA, power, performance, and area, along with a growing set of users. So the architecture of Open Road software has also evolved substantially for quality, maintainability, and development velocity. There's now just one repo with only one submodule. Logging, CI, dashboards, and metrics collection all support our bring up of intelligence and automation, which is our ultimate goal. And this is a picture from eFabless showing their MPW-1 shuttle in Sky 130. There were 40 plus tape outs made with eFabless's Open Lane, which heavily uses Open Road. And here's a gallery of some test cases. You can see macros or with and without macros in 12 and 65 nanometer. These have Open Road generated fill. They're clean on all timing, DRC, LVS, ERC, and antenna checks. And the validations are by our project's internal design advisors team with commercial sign-offs, as mentioned in the slide. So phase 1 focused on automated RTL to tape out clean GDS, but PPA is our focus in our current phase 2A. That's year 3, basically. The main vectors include synthesis, placement, clock tree synthesis, and optimization in our resizer, plus learning and insight that we get from metrics collection infrastructure and large designs of experiments. So we feel that for PPA, we have a lot of low-hanging and some not so low-hanging fruits to harvest this year. For that single core Black Parrot that I showed, several tool updates, improving some levers like sync clustering in CTS, and simply starting to aim for better Fmax and density already show some significant improvements. And these are the green numbers relative to the past October's black numbers. And you can see improved wire length and skew and a 36% improvement of effective Fmax. And let me say a bit about one of our PPA vectors in clock tree synthesis. This is just an example. Our on-the-fly characterization for buffering is now more accurate. It also eliminates a tool setup pain point for users. Cleanup of top-down sync partitioning reduces latency by up to 50%, and turning sync clustering back on reduces tree depth and skew. So these blue and green highlights show promising wins for CTS skew and latency relative to the previous baseline. And we also do see instabilities, just like you'd see in commercial tools, and we continue to track these down. There's also new logger support plus visualizations in our GUI. Here you see the whole clock tree and just the top level to help analyze and debug, both as developer and as user. Using resources at the San Diego Supercomputer Center, at Michigan, or in Google Cloud, we can collect thousands of synthesis, place, and route run data points in a day. For synthesis with Yosis and ABC, we've studied eFablis's recipes alongside our default recipe, which comes from the synthesis experts who have newly joined our team. And this is a rapidly moving area, actually, in the project. In these charts, 22 recipes are sorted by worst negative slack, which is on the y-axis. So lower y values are better. And for the IBEX RISC-V core in GF12 and Sky 130, our default recipe looks pretty good. But we also see the need for having designed adaptive recipes and smart cocktails or shotguns of recipes. So that's ongoing work. We also use big DOEs to study trajectories of QOR and uncover flow issues. So the upper right picture that's being shown shows benefits of higher utilization. The lower right shows how our platform run script might stack up against many possible settings. So it's the yellow circle, which has pretty good slack and area properties. And the colorings show how post-CTS slack on the x-axis is an early indicator of router failure. And this kind of experiment allows us to ratchet up the baselines for our test cases. My last example shows how synthesis target tracks through netlist or post-place opt or post-CTS stages. The wider range of outcomes in the red arrows when RTL to GDS is pushed harder is just like what you see in commercial tools. And a big research challenge for us as a research project is to intelligently manage and exploit populations of these trajectories within a given compute resource. Okay. Say a little bit about metrics collection. Metrics collection enables tool improvement, and it enables machine learning to have a smarter, more self-driving tool. And this has advanced a lot in recent months. Our tools now, or all engines now, use the same logging API and nomenclature. And we've been evangelizing our metrics naming convention and approach to both researchers and industry, whether SI2 or the IEEE Council on Electronic Design Automation, because right now there's no standard platform out there for EDA and its users. And in Open Road, this infrastructure serves many purposes, from dashboards to analytics. We currently collect metrics at different flow stages across platforms and across test cases. These clips illustrate the consistent message types and logging that support metrics collection, and it's evolving, but you can see the flavor of consistency and style that's easily mineable and collectible and mineable. So this supports metrics collection. And now I'd like to switch gears a bit. Also, this is the transition to Tom, who'll take this talk the rest of the way. I'd like to remind that Open Road development has to achieve critical mass, critical quality, maximum velocity, maximum openness, has to support clean foundry tape-out automation and the needs of early adopter users, which is why our project, which aims for no human in the loop, has a very capable GUI. And so let me sign off with a video from Matt Liberty.
The Open Road GUI serves the dual purpose of allowing users of Open Road to investigate their designs and developers of the Open Road application to investigate their algorithms. Here is a design in which the user can zoom in, they can pan, they can select individual objects for further exploration. The selection here is showing what's been selected. Net instances are selectable. In addition, full control over visibility is provided. The developer can also use it to visualize their algorithm. Here is an example of the global placer placing. The green objects are the placeable objects. The algorithm is running live and updating the GUI as it proceeds. In addition, it's possible to stop with the live GUI and investigate the individual objects within the design, and even to continue the algorithm on.
And let me turn the presentation over to Tom.
Okay, thanks, Andrew. So I'll show.
The Open Road GUI serves the dual purpose of allowing.
Thanks. Okay, perfect. So I'll show a little bit more about the GUI and then go on and talk about other topics. So here you can see the GUI being able to support RDL, showing 45-degree geometries. This is built on top of OpenDB. On the right is dummy fill for Metal 3 and GF12, showing both the OPC and non-OPC shapes. Here, Andrew had a small version of this. This is the clock tree, both the placed and routed version of the clock tree. This design is Black Parrot in GF12. This is the one that Andrew had talked about that we took all the way through to clean tape out. So here we see visualizations of the post-global route congestion. And again, just to remind you, all these screenshots are taken right out of the Open Road GUI itself. And there's a lot more, and it isn't easy to extend architecture. So as more people contribute to the project, people may come up with ideas for what they want to see visualized, or especially visualizations like Matt showed of the algorithms running themselves for debugging purposes is turning out to be really helpful. The architecture is rapidly advancing. For instance, we want to support front-end designer use cases, to have a schematic viewer, a timing path viewer, for example. So a fantastic milestone for the research community is the long-awaited open sourcing of ASAP 7 from Arizona State. This is a highly realistic PDK with 7.5-track libraries in multiple VT flavors and full design enablement. One click, and a 6-track library is also near completion. So continuing on with ASAP 7, we're working on supporting memories. So the SRAM circuits and layouts have been finished. Timing characterization flow using Cadence Liberate is in progress now. And register files, ROMs, CAMs, and TCAMs are also in progress. And we see ASAP 7 as a great platform for open collaboration and system exploration, and including this vibrant open source hardware community. People could do designs with this, and it looks like a real process. It's also going to be great for us to have regression tests. So on top of that, Larry Clark's team has been moving really fast since joining the project. ASAP 5 will also be open sourced in the future and will use horizontal nanowire transistors, and the ground rules, track boundaries, advanced node scaling boosters such as single diffusion break and contact over active gate. A 6.5 track cell library and physical verification are well underway. At the bottom here, you can see a D-latch layout and an SRAM cell array. So IceWall is how OpenRoad supports SoC integration and planning. It allows encapsulation of technology and I/O library to minimize the information needed to automatically construct a clean pad ring. IceWall now supports pad ring construction for both wire bond and flip chip. The tool decouples two elements, a physical footprint file and a signal mapping file, to support pad frame reuse. The figure here shows main inputs, Verilog, signal mapping, footprint, I/O library, and that the footprint file can be automatically extracted from a previous layout depth if there is one. Here are some screenshots in GF12LP, staggered pads as well as flip chip, and also another screenshot from Skywater 130. Further automation and support for system on chip design is in the roadmap. Another technical highlight is our release of the Open RCX extraction tool, which comes from donated industry code. A PhD student worked with the original developer to improve and integrate this into OpenRoad. It has been brought up on these technologies shown here. These plots show recent GF12LP resistance and capacitance correlations versus the commercial tool. And here is endpoint slack correlation between an Open RCX plus Open STA extraction and timing flow versus a commercial extraction and timing flow. OpenRoad has 16 tasks, and there's a lot we can't even begin to tell you about today. Please see our paper. We have multiple papers that we've published. One thing that I would like to highlight is that OpenRoad is unique in that it's a partnership between EDA academic research and industry veterans. You saw from Andrew's introduction that we have team members from several universities performing core research, large industrial semiconductor companies providing guidance and priorities, and industry consultants with extensive EDA experience performing key development. This unique project and blend of expertise is focused on breaking new ground in terms of automation of RTL to GDS2, and also creating a robust industrial quality piece of software. So it can be a basis for industry relevant research and usable for important target users like the defense industrial base. It also documents in open source form how robust EDA tools are put together. So one more slide forward. And Andrew and I have provided some links for you to explore at the end of the presentation. Thank you very much.
Thanks both for an excellent update and information on the OpenRoad project. I think it's very exciting what the team has been doing and providing to the industry, and it certainly helps illustrate to many the complexities involved in the physical implementation and analysis space. I have one question here from the audience, which is, are you guys working on in-memory compute or doing any collaboration for it on SRAM or Flash using Open Road?
I typed in an answer while Tom was talking, but at a high level, not specifically in-memory compute, but we do see folks trying highly tiled AI ML architectures, which are extremely SRAM dominant. And one example would be with performers in the real-time machine learning program. And we do think about front-end SoC support, or the support for front-end chip planning and even design path finding, like architecture exploration, quite a bit, but not in-memory compute per se.
Thank you. I had one question. I was curious as to what the user experience has been, or if there's much user experience in this arena in terms of developing their own recipes or cocktails using the bindings that are present in Open Road.
I guess I could take that one. So we do have a few users, and we actually have 3 users. You saw eFabless and all the tape outs. If you lump that all into one, which is really 40 different users, but we do have some users who are modifying the code, creating their own scripts. You can see that eFabless put OpenLane together, which is a recipe which is very targeted at Sky 130. So we definitely do have people creating their own recipes, and we try to collect the best of those recipes and put them into Open Road. If somebody is doing something complicated with a script, we try to pull that into the application and make it a command. So yeah, definitely we have people doing customizations.
Thank you. I have a question from the audience, and that is if there is support for VHDL.
At the moment, we do synthesis through Yosys, which does not support VHDL.
Okay. Let's see. And then I had another question is, do you envision at some point that a foundry might start qualifying the tool stack? As you probably both know, that the foundries typically will qualify a given application or application stack as part of their process qualification.
Sure, and that type of process and application of those resources usually customer driven. So I hope that that will happen in the future. We haven't seen that yet, but as we get users using Open Road to tape out to various foundries, and the foundries see that there is a demand there, then I think that's something that would be very helpful to push for.
Okay. I had one question that came in on the chat, which was, how can we get at least decent non-manufacturable PDKs like ASAP7 or older technologies like GF12 or TSMC45 under fully open source licensing terms? That may be a difficult question to answer, but I will put it out there.
I think it's a difficult question to answer, yes. I mean, if you look at the history of how ASAP7 was developed by ASU and ARM, even the sort of clean room approach that everything had to be publicly sourced that went into the technology definition and the ground rules definition is a really high bar. And there are the free PDK 45s and 15s. There, I think people have kind of mentally moved on. And so it's unlikely, in my opinion, that people will invest a lot of volunteer effort to bring up, let's say, an equivalent ASAP 22, for example. But that's my personal opinion. Everything's solvable with resources and incentives, so that's up to the community, I suppose.
I was just curious as to, I know you mentioned that the software stack is running in Google Cloud, just in terms of the scale out capability of the software stack, if you can comment on that a little bit.
Sure. So I think We definitely use Google Cloud heavily for our CI, and like Andrew mentioned, gathering the metrics, running thousands of experiments. You know, built into the software itself at the moment, it is heavily multi-threaded and it can scale pretty well up to 24 threads. We aren't yet taking advantage of doing massive distributed runs natively, but in our scripts, up in the Open Road Flow scripts repo, we definitely do take advantage of running many jobs in parallel.
Very good. Well, I don't have no further questions, and I really appreciate the excellent presentation and the work that you both have done and the team on Open Road. So thank you so much.
Thanks for having me.
Thank you.
Yep. Our next speaker is Brian Faith from QuickLogic, and he is going to be talking about open source FPGA tooling.
All right, can you see my screen?
Yes, and hear you too.
Great. All right, well, good morning or good afternoon, everybody. I'm Brian Faith, the CEO of QuickLogic. And the last time I spoke with the CHIPS Alliance, it was around the fact that we had taken this big step into open source FPGA tooling coming from a proprietary tools past. And so this presentation is sort of the next step in the journey along those lines. And so for those of you that don't know, QuickLogic is a fabless semiconductor company. We started as an FPGA company, and today we have discrete FPGAs, we have MCU plus embedded FPGA SoCs, and then we have an embedded FPGA IP business as well. So programmable logic is sort of the root of everything that we do, and so it's fun to talk about this in the open source context. So when I started at QuickLogic 25 years ago, everything that we did was proprietary. We didn't necessarily do it all ourselves. Sometimes we partner with other companies, but every element of the tool chain was in fact proprietary. And so starting as an application engineer, one of my jobs was to build out schematic macro libraries that would then go into the schematic tool and write Verilog simulation models that would go into simulators, and then have to validate all of these different design flows from different vendors for Verilog and VHDL and schematic capture with folks like Mentor Graphics and Cadence and Synopsys. And then, of course, all of that sort of comes into the proprietary place and route tool in the middle there in the brownish colors to create a netlist for a customer so they could actually program a part. So there's lots of moving parts there, many of which are not ours, and all of which were proprietary. And it was interesting because I actually taught a programmable logic class at Santa Clara University probably about 20 years ago. And I can tell you that most of the time spent creating the curriculum for the class and the labs and so on was really about how to take the same design and run it through several different vendors' tools. And if you think about that, that's really not a value add for the student. They should be learning about how to use programmable logic, not how to use each and every vendor's tool. But it was required because everybody had their own tool flow. And so, you know, that kind of begs the question, why do FPGA vendors do it this way? And I can tell you why, because we are a vendor like this. Humans like routine. We like to do the same thing, generally speaking. Change is definitely painful, and change is risk. And if you think about engineers that are building products and putting them into systems that like flight control of airplanes or industrial equipment, you don't want to take a lot of risk on something that you may not know. And so the FPGA vendor in the world for the entire existence, and there's been, you know, over 60 of these companies that have come and gone in the last 30 years in this area. It's really this robust software that we have, and there's no incentive really for the FPGA vendors to change, because the notion of this proprietary tool chain really is that walled garden. And so people get accustomed to it. Again, they don't like change. And so it just sort of perpetuates that walled garden approach. So the last time that I presented, as I said earlier, it was really about this first step that we had taken in an open source tooling support of our devices. And as I've credited many times, I'll do it again here publicly, you know, Tim Ansel and his persistence in convincing myself and QuickLogic that this was the right thing to do is why we're presenting the slide today. And many of the folks over at Antmicro helping take our architecture and bring that into the open source tooling domain. So today in this particular chip showing here, we have a microcontroller, an embedded FPGA block. It has SymbolFlow support, it has Renode support, and it has a variety of real-time operating systems that run on the ARM core. So Zephyr and then FreeRTOS, and we have that little dev kit up there in the upper right. So that was a year ago. So what's sort of happened in the last several months is that the tool chain is starting to get filled out even more. So now in MyGen and MicroPython and TensorFlow Lite's running on it, and we have all these other dev kits. And the interesting thing for me is that, again, coming from this proprietary past, there's just everything that we did for ourselves, and it was closed and proprietary. And now we're starting to see this virtuous cycle of people starting with things that are on GitHub and then adding to that and improving it and porting new tools on top of tools. And I know several people on this call are part of that, and I'd like to express my gratitude to the community for making that happen. But you can see now
Hey,
that,
Brian,
yeah.
your slides are not advancing. I don't know.
No.
Oh, there we are. Okay.
Okay, well, great. Wrong screen. Thank you. So this was that graphic on the FPGA tools of being proprietary. This was the slide on why vendors resist, walled garden. These are the tools from a year ago. As I said, the SymbolFlow support for the embedded FPGA, Renode for the whole chip, the real-time operating system support in the ARM core. And then today, really getting filled out further with TensorFlow Lite and MyGen and MicroPython. So now you can really start seeing this virtuous cycle happening, which is sort of exactly what Tim Ansel had talked about, and it is happening. And then I think the really neat thing for me personally, and then this sort of goes back to the fact that I did teach that programmable logic class and have a strong connection with my university still, that now one of these companies that works with us has actually taken SymbolFlow and started to run it on an Android smartphone and on Raspberry Pi. And they're getting this into the curriculum now in IIT Hyderabad in India. And when you think about like what that opens up the capabilities now, where somebody could literally take a $10 dev kit with open source software and start doing FPGA design with their Android phone, which, you know, so many people in the world have an Android phone or Raspberry Pi, it really opens up and truly democratizes the capability to use this technology for cool and interesting and learning purposes. And to me, that's so powerful. And it's so neat to watch that kind of thing happen. So I think this is just going to start and perpetuate further. Bringing it back to QuickLogic, we have our own roadmap, and you know the previous chip was around ARM, and this next one is around RISC-V. And so in this, there's already Renode support for this and SymbolFlow support for the embedded FPGA. But I think that one of the neat things about the open source tools here is that it actually makes it very efficient for us, QuickLogic, to do architecture exploration. So, you know, as we look at these different use cases like visual wake words with TensorFlow Lite for microcontrollers, and we start mapping it to this architecture on the right, you know, in the past, if we wanted to do proprietary tools only and working with proprietary synthesis vendors specifically, we'd have to go and take a lot of time and a lot of money just to try little different changes in the FPGA architecture that they would then have to map to or infer blocks for, and then see what the net result of that was. And so with these open source tools, that's sort of within our control now, or a much stronger degree of influence to do that architectural exploration and optimize the architecture for the algorithm versus the other way around. And so this is, I think, again, it just speaks to the power of open source. And so just sort of wrapping it up on this whole thing, and I think a lot of this sort of comes down to changing our mindset. And I know for us, it took like a year of that, talking with Tim to get to that point of having this different mindset. But for FPGA companies in general, there's a massive NIH factor here of trying to say that proprietary tools are not as good as open source tools. And so I don't know how we overcome that, but I think there's a lot of work to be done there just in general to convince people of that, and to convince them that there's more upside than downside. I think anytime you have a walled garden, when you start thinking about breaking down those walls, that's viewed as risk. And so how people can view this as more gain than pain, I think is important, not just from the FPGA vendor, but from the users as well. I think a lot of users that are software savvy, like these new tools and flows, I know a lot of the quote unquote older or more experienced FPGA people that grew up with this normal old flow, they're going to have some hesitance to switch over to these new flows. And so I don't know how we do this, but how we make that pain low and the gain high, I think is going to be really key to getting people to embrace these open source tools even more than they are now. And I think it will happen. It just takes more persistence and creativity from the community to do that. So we're on board. We've completely switched from our proprietary tool to open source tools, which I'm really happy about. And that's allowed us to do things like these devices that I just showed you, the roadmap devices. For our embedded FPGA IP cores, we can very quickly spin up software support for a new core that a customer of ours may want. We were able to participate in the eFabless Google Skywater 130 Open MPW project as well, which we would not have been able to do without the open source tools. That was really the enabler for us to quickly participate in that project, which I'm pretty excited about. So anyway, I think the future is bright. We're really excited, and I have absolutely zero regrets about moving into this open source direction, because it's the right thing, and I think the industry will catch up eventually, just not quite yet. And that is the conclusion of my slides, and I do apologize for being on my wrong screen as we advance through these. Any questions?
Thank you so much, Brian. I appreciate the update that you provided. I'm just curious, does QuickLogic itself do development of open source FPGA tools or help support that?
Well, we support it in the sense that we've worked with Google and Micro quite heavily in the last, I would say, year and a half on getting our architecture support in there. I would say that contribution-wise, there's been more from the community as far as improving the tools. And it's not because we don't want to, it's just because we're still shifting the mindset and the skill set from the proprietary development to open source. But we're definitely making contributions in that area. And like I said, every new device or core that we do today is in open source tool support. We're not doing any more proprietary development in that area.
Interesting. And then what about, do you provide some type of reference flows for your customers for the open source tools, or?
Yeah, we have on our GitHub repo, we have a whole section on user, I don't forget the name of it. It's a quick start user examples that you can actually take the flows, download them, install the packages, and there's reference code or designs that you can take through the flow. And we actually have a lot of webinar videos now that we've been recording over the last, I would say, month and a half, almost like one a week, to give people, just the flows and show them how it's done. But all that code is on our GitHub repo.
Listen. So I have a question here. Did the quality results improve or degrade when switching to the open source synthesis and place and route tools? Are they on par with the closed source counterpart?
That's a great question. And I meant to actually include that in my slides. So when we started, actually, let me just take a step back. So at the OR conference in 2019, I remember I think Dave Shaw was presenting some results on place and route and how he was tracking to proprietary tools. And that was one of the data points that we used to make the decision to go into this whole thing. With respect to our architecture, our devices for reference tend to be on the smaller side of the mainstream FPGA market. So we're talking about, thousands of LUTs as opposed to millions of LUTs. And so for designs of that size, the tools that we have access to the open source tools, they're on par with the proprietary tools. In fact, I think it was like plus or minus 10% or less variance to that, depending on the design. So that was one of the data points also that made us comfortable that we no longer had to do proprietary tools. So we used to bundle precision synthesis from Mentor Graphics or now Siemens, and we no longer do that because the Yosis and SimpleFlow are very good from a quality result point of view.
Thank you.
Yeah.
Another question that came in was, do you support different FPGAs from Xilinx or other companies?
Well, we sell FPGAs and IP cores, so I don't support competitors' products, but these tools do. So SimbleFlow, and the next presenter is Tim Mansell, who's very, he knows SimbleFlow better than anybody. I think he could probably comment on that support for Xilinx, but QuickLogic itself does not support Xilinx, nor Altera,
Sure.
nor any of those other competitors' devices.
Makes sense. And then here's just a comment by another person, not a question, but more thought. Regarding changing mindset about open source EDA tools is to get companies to donate development resources in the same way the Linux core is developed. So,
yeah, it's a good thought. I agree.
Thank you again so much for your time, Brian. I appreciate it, and the presentation. And our last presenter today is Tim Mansell from Google, who is going to talk about fully open silicon down to the transistor. So, Tim?
Can you hear me okay?
Yes.
And can you see my screen?
Yes, you're a little bit over amplified too, by the way.
Let me just see. How about now?
A little bit better. Let's try this.
Okay. Sorry, let me. So, the topic I'm talking about today is fully open silicon down to the transistor. That is a pretty long topic. So I did a full paper on this at ICCAD 20. And so if you want to get a much more detailed information about some of the stuff my team is doing at Google, you can go and read that paper. I also want to say that I'm a software engineer. I'm not a hardware engineer. I self-identify as a software engineer, and I'm only a newcomer to this hardware design space. I'm not a newcomer to open source. I've been doing open source since 1995, back when Linux was, this fresh new thing that was battling these old traditional Unix vendors, of which very few still exist. And I've been at Google for a long time as well. I think it's actually almost up to 13 years now. And one of the things that I know about Google is it runs on computers. Google kind of pioneered this idea of using lots and lots of computers to do distributed tasks, especially commodity off-the-shelf computers. And it uses a lot of them. This is probably a smaller of the data center type pictures. However, as we all know, Moore's law is kind of no longer giving us the free ride that we used to get from performance increases. The problem with that is that demand for compute power at Google continues to grow exponentially. And previously we were able to keep up with it thanks to things like Moore's law. But now we're increasingly seeing that we're going to need to do a lot more hardware design to make it possible to keep up with these demands. And one area that we have been highly successful, and I wasn't involved at all with the TPU, but TPU is a really great example of being able to scale to the growing demand for ML compute, which was growing at rates of like 10,000x, to keep up with the demand by using specialized hardware. And the team who does this has done an absolutely impressive job. But they have definitely felt the fact that as the TPU design has gotten more complicated, verification costs and design costs have gone up. There's also quite a big gap between what you could ideally get in a process technology and what you actually get. And so my team was started to look at how we can enable people at Google to do ASICs like the TPU without needing a team like the highly experienced team behind the TPU. And so we started by looking at what you need to build a ASIC. And you kind of need three parts. Coming from an open source background, I was very interested in understanding if these parts had open equivalents. And it turns out for a long time, there has been actually quite a thriving open source IP library ecosystem. And the recent success of RISC-V has actually made that explode massively. There's now a really big thriving ecosystem of fully open source IP. As we also heard, thanks to DARPA's IDEA program, there is a massive amount of improvement in the open source EDA capabilities. But what we found was that there wasn't really any open source PDK. If you think about what a PDK is, it's all the kind of low-level details needed to actually create a device. And like, since you want to actually create a device, this data is really, really important. And when we looked at what open source PDKs existed, there was a whole bunch of stuff that exists, but it was non-manufacturable, and it frequently had restrictive licenses. When I wrote this slide, a SEP 7 was under a restrictive license, but now that's under a fully open source license, and I'm really glad Andrew managed to do that, but it's still a non-manufacturable PDK. And as a consequence, if you look at like eFabless, they created a open source design called Ravina, which had fully open source RTL, used fully open source tools, but because they used the XFAB 180 PDK, which was not open source, the PDK data effectively infected the rest of their design and meant it so that they couldn't release a system that anybody else could just take and tape out at XFAB straight away without having to think at all. And so we got thinking and the thought that the lack of a manufacturable PDK was one of the biggest blockers towards having a fully open source IC. And so this fully open source roadblock was something we thought we could do something about. And so after a lot of work, I managed to find a foundry that was willing to collaborate with Google, and together with Skywater, Google released what I believe is the first fully open source 130 nanometer manufacturable PDK. And when I say fully open source, I mean it's licensed under Apache 2 license. You can just go to GitHub and you can clone the repo and all the data is there. There's no NDAs to sign. There's no lawyers to be involved. It is a thing that you can just get started with without having to ask anybody's permission. And the PDK includes quite comprehensive support for the type of things you might want on a 130 nanometer node. The Skywater process is a fairly expansive process that includes things like inductors and high sheet row polyresistors, MIM caps, Sonos shrunken cells, high voltage support, including 5-volt IOs, high voltage extended drain NMOS and PMOS. And so that's really cool. But coming from a software world, I got really frustrated with the fact that all the documentation was delivered as giant PDF files. And so we converted the documentation to be like what you'd find with a modern software project. It's hosted on Read the Docs using Sphinx. This is kind of what the documentation looks like, and it's publicly available and searchable with Google. Here's some, information about the various design rules you have to comply with. And these are kind of the low-level details about exactly what is and isn't manufacturable. There's stack-up diagrams, but that by itself isn't enough. So there's also digital standard cells, there's IO and periphery cells, there's a full set of base primitives and DRC rules, there's analog RF primitives, and there should be a SRAM and flash build space anytime real soon now. That's been pending a while, taking a lot longer than I had hoped to get released, but that's definitely coming. And we've already seen certain things be released there. We also don't have just one standard cell library. We have a lot of different standard cell libraries, which have quite a comprehensive list of cells. And you can kind of see how the different standard cell libraries are optimized for different use cases. The high voltage one is obviously optimized for high voltage. And I don't have to be scared about showing you this GDS. This is a cell from Skywater. I have no idea what this cell is, but I'm sure all you, ASIC designers there can tell me what that is. But I can just share it with you. And this is the SRAM bit cell, both in single port and dual port variants, and you can see that it's significantly smaller than the D flip-flop cell on the Skywater process. And the thing is, you need to build a full memory out of this, and so I'll talk a little bit about that in the future. And we're also doing things like trying to automatically generate symbols and schematics of all the parts in the system, because we want people to do more than just digital design. We want people to evolve the PDK, including the standard cells. And to prove this possible, we worked with James Stein from OSU to develop a completely new open source PDK, standard cell library for Sky 130. And so this shows that it is possible to create your own standard cell library with the PDK that we have. And with the Google and Skywater 130 nanometer PDK, you can now have a fully open source ASIC. And I think that's a pretty cool achievement. And so that had a lot of contributions from a whole bunch of different partners. But what I really care about is the ecosystem. And, how do we grow the ecosystem? Well, we started out by taping out some chips to prove that you could do this. We also did a talk series, which currently consists of 7 talks. But I also launched a fully open source shuttle program. This is not your average shuttle program. We're taking a very different philosophy here. We want your prototypes to be considered throwaway and not uniquely precious. There's this kind of thing where currently, when you get back your prototypes from an MPW run. You know, you mount a couple on a board and they become the most precious things on the planet. You let none of the interns near it because, you know, if they spill coffee on it, it's the end of the world. What we want to see is that your prototypes are, you know, shareable. You have plenty so you can give them to people. And we also want to see you fail, not because you're, you know, doing things poorly, but because you're trying things that have never been done before. There's this kind of idea in Silicon Valley that, you know, if you're not failing some of the time, you're not trying things hard enough. And so we also want to make this open to anyone, whether you're academic, maker, hobbyist, commercial, startup, it doesn't matter. You can participate. And to participate, your design has to be open source, and there'll be roughly 40 slots per design. And you go to eFabless and you submit the design. And there's a common harness which allows us to have a standard packaging system, and also to give you a lot of functionality like an in-IC logic analyzer. You still get plenty of space, 10 millimeters squared, and our aim is to get you back 100 packaged, ready to go ICs. This is a kind of an example of the user space and the harness. And you can go and read about the harness. And we want to do multiple runs. The first run, November 2020, second round, mid 2021, and a couple more in 2021 and 2022. If you're paying attention, you might notice that November is in the past. And so we had 40 designs go out on MPW1, and they come from a wide variety of different types of designs. We had processors, we had crypto miners, we had radio receivers, a whole bunch of analog, a whole bunch of FPGAs. And so that was really, really cool. But I think one of the coolest things was 60% of designers had never done an ASIC before, had no experience doing an ASIC. And the MPW1 was their first ASIC they ever did. And I believe even one of the MPW designs was done by a high school student. So that is pretty cool. I'd also like to say, you know, the Chisel graph is definitely pretty impressive, but I think the Skywater one is a little bit more impressive. It really shows how much pent-up need there was for a fully open source PDK. And we see this from our Slack channel as well, which anybody in the world can join. It has over 1,000 members. And the analog design channel alone has over 400 members. And we're getting, you know, roughly 200 new people every 2 weeks download the PDK who have never downloaded it before. And that's pretty amazing to me. And like, we're seeing, you know, 1,700 or, you know, about 800 downloads every week of the PDK. And so this is definitely very different to what people have previously said is possible. So I highly recommend that you join our mailing list and join our Slack and get involved. And we've removed one of the roadblocks that I believe was preventing a lot of new innovation. My ICCAD paper, though, identified 4 roadblocks that were discovered. So if you go and read my paper, you can understand all 4 roadblocks. But to quickly go through them, one of the big things was place and route tooling, and we've been collaborating very heavily with the Open Road project to improve the quality of the tooling and make it work really well on Sky 130. I know the System Verilog topic came up multiple times, and we're investing very heavily in improving System Verilog support in the open source tools. In fact, we're investing so much, we have 2 passes. One is targeted at developer tooling for things like linting, formatting, and indexing. This is interesting in it's supposed to be able to handle unprocessed code. With the way the preprocessor works, it can be possible to make invalid system Verilog code that becomes valid after preprocessing. And so this is Google's Variable project. But we're also working with another parser called Shorelog to create a fully open source simulation and synthesis tooling. And so we're trying to separate the parsing from the backend tooling and use a thing called UHDM to do that. And Shorelog is bolted onto the front of both Yosis and Verilator. And Antmicro demonstrated some very interesting results of being able to use this to work with the IBEX core. And we're getting very close to being able to do the full OpenTitan design and working very hard to make that happen. We also identified that there was some missing IP. We've been working with OpenRAM to make a fully open source memory generator, and hopefully that will also include Flash. And we're working to publish both pre-compiled macros and allow custom macros to be generated easily. We're also excited about applying this generation approach to analog, because analog is one of the big points. So we're excited to see the CHIPS Alliance bringing up the analog stuff. Thanks to Bora, who was our first presenter, we're now seeing a lot better support for BAG on Sky 130. The big problem with BAG is that it still requires a few closed source components. We're hoping to work with Bora to fix that in the future. But I'm also excited that our collaboration with FASOC has resulted in FASOC running on top of OpenRoad. So the FASOC approach to fully open analog generation is now fully open source with no dependency on closed source tools. And I think this is a really interesting milestone that Mehdi, who has been the main driver behind this, has achieved. You know, it builds on top of the work groups like OpenRoad has done, but really now enables mixed signal simulation and to more rapidly iterate on analog design. So again, if you want to get all the details, go and look at my ICCAD 20 paper, and to get notified, join the mailing list and join the Slack workspace. And I'm excited to see all these CHIPS Alliance projects, you know, working with the Skywater PDK, and also hoping that we can do even more in the future. And I think I went 5 minutes over time, but it's hard to cover all the exciting things that are happening in this space in only 15 minutes.
Thank you, Tim. No, actually, you are good on time, but you do have some questions, so thank you. So the first question I have is, does power modeling belong in the PDK?
Yes. That's a simple answer. Yes, it does. I have no idea if it's there or not. I hope it's there. As I said, I come from a software background, so I don't know, you know, what is there at the moment. If it's not there, I would love to have it added. It's mainly driven though by people contributing. As I said, there's a lot of things happening and I'm responsible for a lot of them. So I don't have time to do all the work by me. And so I'm really looking for collaborators and other groups to work with us on this stuff. Yeah, that's why Chips Alliance is so important.
Okay. Next question is, does OpenLane support proprietary PDKs like TSMC, and can and can someone use Sky 130 on proprietary tools like Cadence, etc.?
Open Road is regularly used with proprietary PDKs like the Global Foundries 12 nanometers PDK. I don't know about the older ones, but apparently Mohammed Qassam is just saying yes. GF 130 and XFAB 180 have apparently been done with Open Road, but I don't know anything about that. My group is very strongly focused on the open source aspect of stuff. We don't prevent people from using the Skywater PDK with the proprietary tools like Synopsys and Cadence, but they're not a high priority for us. And people have been slowly adding and improving support there, but it's not a high priority for us. I'm very supportive of it happening. And I do think the closed source tools aren't going anywhere. I think they have a long future ahead of them. I just think the open source tools need more work and more help. And so that's where we're concentrating our effort.
And then I have a question as to VHDL support.
Google is a system Verilog shop, which is why we're concentrating so heavily on system Verilog tooling. However, I do know that there are multiple groups who are very interested in VHDL, and there are multiple people who taped out VHDL designs on the first MPW. I don't know exactly how that was done. I just know it was done. And I know that Microwatt from IBM was taped out on Sky 130, and Microwatt is VHDL. So there's definitely ability to take VHDL designs and get them onto and into OpenLane. But I'm not the right person to ask the technical details of how to do that. If you go and ask on the Skywater Slack channel, I believe there's even a dedicated VHDL channel on the Skywater Slack for people who want to do VHDL stuff. So jump on the Slack and ask it. So yeah, and you know, Microwatt was probably one of the most complicated CPUs that was put onto the Sky 130 MPW1. And so it's definitely pushing the boundary of what can be done there. And I'm hoping that we can convince IBM to, for example, join the Chips Alliance and, you know, start contributing the type of resources Google's contributing to the system Verilog ecosystem to VHDL ecosystem, because I know a lot of IBM's internal work is done in VHDL, and they have a lot of interest in VHDL. So if you know anybody at IBM, go and nag them to join the Chips Alliance and nag them to support open source VHDL tooling. I would love to see some corporate members stepping up to help fund the VHDL language. At the moment, it's entirely driven by, I believe, community and academic contributions. So it could be supercharged by having, you know, people invest in it.
And one final question. Do you think that some other company will open source a PDK or collaborate with Google to open source a PDK like Skywater has done? What are your thoughts or forecast on that?
So definitely, I'm looking for Foundry number 2 to release a another PDK in the kind of 180, 130, 110 nanometer space. I'm also working with Skywater to get their 90 nanometer process fully open sourced, like the 130 process has been open sourced. You know, I want to see a growing ecosystem. I want to see multiple foundries supported. I want to see foundries from the US. I want to see foundries from Asia. I want to see foundries from Europe. I also want to make it really easy that people can use the right foundry for their job. You know, Skywater specializes in doing a lot of custom things to your system that most other foundries aren't willing to do. And so Skywater has a lot of ability to do things, but that does drive up the price a bit. And being based in the US does drive up the price a bit. And some of the foundries in Asia offer, you know, extremely cheap services with much more limited capabilities, but that could be the right thing for your chip, right? Like your chip might take advantage of these advanced capabilities, or cost might be what you want to optimize for. And so giving people the flexibility to move between these designs and like foundries and move designs between foundries much more easily is one of the key aspects that I want to see happen here. And you know, I worked very heavily with Skywater, but they know that they are just trailblazers here. I definitely want other groups to be involved. And you know, this is kind of a rising tide lifts all boats here. We want to see the industry grow, you know, not 10x or 100x, but like 1000x. And so all the foundries in the world are going to be super busy if we succeed. And so I don't think it's going to be a problem that there are multiple foundries supported. And I would like to say one more question, which is, yes, the fabrication is fully free for the MPW program. I believe we're even covering shipping to you. And our goal is to get you back some boards which have already been, some ICs which have already been mounted on PCB boards ready to go as well. And yes, anyone can participate. The cost is the same, whether you're a hobbyist, an academic, or a commercial company. The only thing you need to make sure of is that your design is fully open source. So if you're an open source startup, you're perfectly fine. If you want to be closed source in some way, you'll need to talk to eFabless about going through their paid shuttle program where you don't have to open source everything. I don't think they've actually launched that program yet, but keep bugging Mohammed until he does, because I want to see that happen, because I want to see as many people doing this as possible. I just believe open source is a really great way of doing it, but I would love to see a lot more designs full stop, whether they're proprietary or open source. And I think open source can help build out a lot of these common stuff that everybody needs, allowing people to concentrate on just the one thing they think they can innovate on. And this will dramatically increase the number of things we can try.
Very good. And just one final question is, do you have a recommendation on a new foundry anywhere that is not sub 10 nanometer?
Well, like I don't have any recommendations, but pretty much most foundries have older process technologies. TSMC, Global Foundries have older 130 nanometer processors, and I think if you talk to Mohammed Qassam, he'll say to you like over 50% of the wafers in the world are done on older than 130 nanometer nodes. And so there's definitely lots of groups out there. There's also groups like Silterra, XFAB, if you're in China, SMIC. There's like lots of others that I'm probably forgetting. If I'm forgetting you, it's not because I don't want to talk to you. It's just that, I have a terrible memory. And I would love to see everyone open source their process technology and enable a new wealth of users to start doing designs on your process. Like if your process is a useful thing to exist, then people are going to want to use it. And open source enables people to use it much more efficiently and quickly. Anytime I have to talk to lawyers, my excitement for doing the project dramatically goes down. And when there's an NDA involved, I have to talk to lawyers. And so, open source makes a lot of this go away. I can just go to GitHub and start doing stuff. I don't need to worry about, the type of problems like finding somebody's phone number so I can call them to figure out whether we can even potentially do a NDA in the first place. And you'll be surprised at how many projects get killed just because of that.
No, that makes sense. Well, thank you very, very much, Tim, for your talk. It was very informative. I really appreciate your time and effort to put this together.
Yep,
and I want to thank
say,
you.
like, this is just the start. I want to see it grow, and if anything like the graphs we've seen are growing at exponentials, we have a really bright future coming up.
Thank you. So I want to thank all the presenters for their time and effort to put the presentations together today. I thought it was excellent material, and also to the audience for their time and interest and the questions I received, and also special thanks to Brian Warner for helping me put this all together and orchestrating all the slides. So thank you very much. So if there's nothing else, we will end this presentation. So thank you.